Hey guys, good morning, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, can you quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you? Can you let me know quickly in the chats? Can you quickly let me know in the chats if all of you can hear me? If I'm perfectly audible, visible to every one of you? Quickly in the chats, people. Welcome back, welcome back, welcome back. Welcome back. So people, as you all must be knowing, today it's going to be our complete class 11th Inorganic Chemistry, right? And from your complete class 11th Inorganic, there will be almost like 30 to 35 marks, which you can fetch from this particular session. So I would definitely want you guys to watch this particular session till the end, because it's not going to be some huge session, 10 to 12 hours. No. The maximum duration of this session will be almost 5 hours. Okay, that's going to be the maximum duration of this particular. And one more thing. On Tuesday, there is complete class 12th Inorganic Chemistry session scheduled. Okay? On Tuesday, my dear students, there is complete class 12th Inorganic Chemistry marathon scheduled. All right? So basically, we are basically done with class 11th physical, except thermodynamics. Class 11th Inorganic will be done today. Class 11th Organic is already done. Class 12th Organic is already done. Now we are technically left with 2 marathons in chemistry. One is going to be complete class 12th Inorganic, which is scheduled on Tuesday. And one is going to be complete class 12th physical, which will also happen next week. So with that, your entire chemistry syllabus will be done and dusted, my dear students. Okay? All right. Yes, I know there is one chapter left in physical, that is thermodynamics. Don't worry about that as well. Okay? As I've already told you, we'll complete your entire syllabus. And we are already almost done with 60 to 70% of that. Just wait for a few more days, everything will be done. I mean, in the next week, your entire syllabus will be done. It will be completely completed. Okay. Before starting this particular session, as you all must be knowing, I start the session with a question. Which part of the country you guys are watching me from right now? I just want to know. I just want to know. Which part of the country you guys are watching me from? I just want to know that. I just want to know that first. Okay, Kerala, Telangana, Tamil Nadu, Jharkhand, Karnataka, Jammu, Shillong, Andhra Pradesh, Kerala, Maharashtra, Telangana, Tamil Nadu, Assam. All right. Indore, Srinagar, Kashmir, Manipur, Meerut, Jharkhand, Maharashtra, Chhattisgarh, and Pondicherry. Someone is watching us from KGF. Yeah. Mizoram. Madhya Pradesh. Okay, and Delhi. Someone is watching us from Andhra Pradesh. Andhra Pradesh. All right. Okay, one more thing, guys. One more thing. one more thing. I am not sure whether you guys know it or not. Today at 5 p.m., there is one more session scheduled. To join that particular session as well. Let me show that to you. What is the name of the session? All organic reactions in one shot. KK sir is taking that. Okay. To watch this particular session as well. On priority. It will cover all your reactions in organic chemistry. This particular session. Just this session. And this is going to be super enough for your organic chemistry part. Already he has completed class 11th, class 12th organic. Now it's a brush up session. And all the organic reactions he'll be taking today exactly at 5 p.m. Okay. And there is one more thing which I would want to share with you. Tomorrow at 8 p.m. I have kept a class, not on YouTube. That is a special class on the Unacademy platform, which is also free for everyone. Okay. That is top 200 questions of your class 11th inorganic. So whatever inorganic chemistry we'll be discussing today, okay, it's extra question practice I've scheduled tomorrow in the form of a special class. I'll be sharing the link of that special class in my Telegram. So if you are not the part of the Telegram channel yet, I would highly recommend you to be the part of the Telegram channel, because in this particular Telegram channel, Wassim Bhat Chemistry Official, I shall be sharing the link. Of the special class which I'm going to take tomorrow. Okay. Link will be shared here on this Telegram. And what is the link for? It is basically the top 200 questions of your class 11th inorganic chemistry, which I have scheduled on the Unacademy platform exactly at 8 p.m. on Sunday. 8 p.m. tomorrow. All right, do join this particular session as well. You have to do nothing. You just have to click on the link that I'll be sharing on my Telegram, right? Tomorrow at 8 p.m. Perfect. After clicking on that link, automatically you can watch this particular session. It's going to be live session scheduled at 8 p.m. tomorrow, right, on Unacademy platform. Okay. Perfect. Should we start then? Is everyone ready? Give me some fire emojis quick in the chats. Someone is saying promotion. This is not some promotion. This is something for you. Okay. It's a class for you. Class scheduled for you. What promotion you are talking? E block will be done on Tuesday session. Tuesday is class 12th inorganic chemistry. That will be done in that particular session. So today is just going to be class 11th inorganic. As I told you, class 12th physical chemistry next week. Give me some fire emojis in the chats, people. Where I am from? I am from Srinagar, Jammu and Kashmir. All right. Should we start then? I think yes. Guys, do not write anything. Okay, do not write anything apart from the topics which we'll be discussing now. Okay, do not try to spam, because you know the people who spam, they get blocked at that instant. So don't try to do that, because I don't want you guys to get blocked. Consider it as a request or a warning, right? The choice is all yours. Okay, perfect. Okay. So today it's going to be your complete class 11th inorganic chemistry. Let's get going with that. Nothing apart from today's session in the chats, I should say. Duration of the session will be not more than 5 hours. Don't worry about that. So my dear students, let me first of all tell you the topics which are there in your class 11th inorganic chemistry. My dear students, the topics which are mentioned here, this forms your complete class 11th inorganic chemistry basic. Whenever question is asked from your class 11th inorganic chemistry, they'll be asked from these topics on whatever you can see on your screen. How to identify the period number, group number of the element, questions based on atomic radius, questions based on ionization energy, questions based on electron affinity, questions based on electronegativity, questions based on how to draw the Lewis structures, questions based on dipole moment, questions based on Pajan's rules, questions based on formal charge, questions based on hybridization, valence shell electron pair repulsion theory, molecular orbital theory, bond angle, and hydrogen bonding. This forms your complete class 11th inorganic chemistry. And my dear students, I shall be discussing all these topics in detailed form in such a way that you should be able to solve each and every question if asked from these topics in your upcoming Re-NEET exam. Okay, perfect. If the question is asked from class 11th inorganic, questions will be asked from these topics on. Just understand that. Remember that. Okay, just remember that. All right. So let's get going with the first topic, my dear students, which is on your screen. What is that? That is, how do we check the period number and group number of an element? And in order to save the time of the today's session, I have got slides already ready-made today. Okay, we are not going to write a lot of stuff on the screen just to save the time, because inorganic, it's all about writing things and all. Okay, whatever things were supposed to be written on the screen, I've already written those things on the screen itself, so that we can save our time in the today's session. So my dear students, first of all, how do we predict the period number and group number of an element? This is the first topic. How do we predict the period number and group number of an element? My dear students, I am going to talk about the first topic now. How do we calculate, how do we predict the period number and group number of an element whose electronic configuration will be given to us? You will be given with the electronic configuration of an element. You will be given with the electronic configuration of the element. And from the electronic configuration of the element, you will have to check the period number and the group number of an element. How do we exactly do that? There are some rules, my dear students, which you have to follow. And what are the rules? Let's have a look. First of all, let me tell you. If the electronic configuration of an element is given, and you are supposed to check the period number of an element, remember, highest value of principal quantum number. Highest value of principal quantum number gives us the period number of the element. Highest value of principal quantum number, it gives me the period number of the element. For example, let's say this is the question that's given to me. I am given with this particular electronic configuration. And from this electronic configuration, I have to calculate the period number of the element. As I told you, period number is nothing but highest value of principal quantum number. So do you see the highest value of principal quantum number here as 3? Right? So I would say the element whose electronic configuration is given to me, its period number has to be 3 only. For example, this is one more question, for example. I am given with this particular electronic configuration. This is the electronic configuration of some element, and I have to check the period number. Check the highest value of principal quantum number here. That is 4, as I can see. So I would say period number of this particular element is nothing but 4. Perfect. Similarly, for example, this is the electronic configuration that's given to me. And look at this particular electronic configuration. I would say the highest value of principal quantum number here is 5. So I would say the period number of the element is nothing but 5. Perfect. So this is point number 1, which I would want every one of you to remember from now onwards. And what is that? Highest value of principal quantum number is always equal to what? It is always equal to the period number. Point number 1. Yes? Perfect. Now, my dear students, point number 2. How do we check the group number of an element whose electronic configuration will be given to us? The first point was how to check the period number of the element. It is always equal to the highest value of principal quantum number. Now, how do we check the group number of an element? How do we check the group number of an element if electronic configuration is given? There are some rules which you have to follow. My dear students, in your periodic table, as you all must be knowing, we have got 4 blocks. S block elements, P block elements, D block elements, and your F block elements, right? And I believe you would be already knowing, in case of S block elements, the last electron enters into S subshell. In your P block elements, the last electron enters into your P subshell. In your D block elements, the last electron enters into D subshell. And in your F block elements, the last electron enters into F subshell. This is something which I believe every one of you would be already knowing, right? Now, my dear students, in case of S block elements, remember, group number is always equal to the number of electrons in NS orbital. Group number is always equal to the number of electrons in NS orbital. What does that mean? Try to understand. For example, I am given with the electronic configuration of the element like this. Let's say this is the electronic configuration of an element that is given to me. And from this electronic configuration, I have to check the group number of an element. So my dear students, first of all, before talking about the group number, if I ask you what is the period number, highest value of principal quantum number, so period number is 4. Period number is 4. The last electron is in s subshell, so I would say it is the s block element, right? And in case of s block elements, how do we get the group number? The number of electrons in ns orbital. If you look at this configuration, this is ns, this is n minus 1 p, right? This is n minus 1 s. Do you understand? So how many electrons are there in ns? There is 1 electron in ns, so its group number is simply going to be 1. Period number 4, group number 1. Let's say this is the electronic configuration that's given to me. The last electron has entered in the s subshell, so it is the s block element. Now, if you look at the highest value of principal quantum number, that's 5, so period number is 5. What about the group number? The number of electrons in ns, so group number of this particular element whose electronic configuration is given to me, that is 2. So in case of your s block element, in case of your s block elements, group number is nothing but the number of electrons in ns orbital. Similarly, in case of p block elements, what are p block elements? First of all, these are the elements wherein the last electron enters into p subshell. And in case of p block elements, my dear students, group number is always equal to 10 plus sum of ns and np electrons. 10 plus sum of ns and np electrons. Now look carefully. Let's say I'm given with the electronic configuration like this. 4s2, 4p2. This is the electronic configuration that's given to me. This is the outermost electronic configuration of an element that's given to me. Now, first of all, they're asking me about the group number. First of all, I have to check whether the element belongs to S block, P block, D block, or F block. If you look carefully, the last electron has entered into P subshell. So it's a P block element. And in case of P block elements, group number is equal to 10 plus number of electrons in NS. This is NP, this is NS. In NS, there are 2 electrons, plus in NP, there is also 2 electrons. So group number of the element is nothing but 14. As simple as that. Similarly, look at this particular configuration. Let's say this is the outermost electronic configuration of an element that's given to me, right? As you can see, the last electron enters into P subshell, so it's a P block element. And in case of P block elements, group number is nothing but, that is 10 plus number of electrons in NS, that is 2, plus number of electrons in NP, that's 5. So 2 plus 5 is 7, 7 plus 10 is 17. So I would say the group number of the element here is 17, right? Similarly, my dear students, guys, I told you already, do not write anything in the chat apart from the studies. I told you already. Do you understand? Do you understand? If you have to discuss any other stuff, you can go to some other channel. I'm blocking few people so that you can get to know. I do not want this nonsense in the chat. If you want to sit in the class, stay silent or get the hell out of my class. All right, let's talk about the D block elements. How do we exactly get the group number in case of D block elements? First of all, what are D block elements? D block elements are the ones wherein the last electron enters into D subshell. D block elements are the ones wherein the last electron enters into D subshell. And the group number in case of D block elements is nothing but, it is sum of n minus 1d and ns electron. Sum of n minus 1d and ns electron. Now, let's have a look. For example, this is the outermost electronic configuration of some element that's given to me. Let's say this is the outermost electronic configuration of some element that's given to me. If you look at this outermost electronic configuration, 4s is having 2 electrons, 3d is having 6 electrons. So that means 3d is getting filled here. 3D is getting filled here, right? So the last electron has entered into D subshell. And if the last electron has entered into the D subshell, so it is a D block element. And in case of D block elements, how do we get the group number? Group number is nothing but it is sum of n minus 1d and ns electrons. So this is ns having 2 electrons plus this is n minus 1d having 6 electrons. So 2 plus 6 is nothing but 8. So group number of this particular element is nothing but 8. Right? Perfect. Similarly, in case of F block elements, my dear students, what you have to remember? Just one thing. Your F block elements, all your F block elements, they will be in group number 3. All your F block elements, they will be in group number 3. Just this thing you have to remember. That's all. Okay? All your F block elements. Atomic number 58 to 71, 90 to 103. All your F block elements, they come in group number 3. That's all. Perfect? So this is how you get the group number of S block elements, P block elements, D block elements, and F block elements if the electronic configuration of the element is given to us. Now the point is, what if the electronic configuration of the element is not given to us? What if the atomic number of the element is given? What if the atomic number of the element is given? Right? What if the atomic number of the element is given? My dear students, if the atomic number of an element is given to us, how do we get the period number? How do we get the group number? Let's talk about that. First of all, there are few things, my dear students, which you have to remember. And what are those few things? Let's talk about them. First of all, identification of the period if atomic number is given. Remember, if the atomic number of the element is between 58 to 71, if the atomic number of the element is between 58 to 71, the element belongs to 6th period. The element belongs to 6th period, and your 6th period elements are called as lengthenoids. Your 6th period elements are called as lengthenoids. For example, let's say you are given with a question. What is the period number of the element whose atomic number is 93? What is the period number of the element whose atomic number is 97? What is the period number of the element whose atomic number is 65? Whose atomic number is 70? I believe you can easily do that. Now, my dear students, if the atomic number is between 90 and 103, if the atomic number is between 90 and 103, the element belongs to 7th period, and you call the element as the actinide. You call the element as the actinide, right? Perfect. So tell me, what is the period number of this element whose atomic number is 93? Atomic number 93 comes in this category, so period number is 7. Period number is 7. Atomic number 97 comes into this category, period number again is 7. Atomic number 65 comes in this category, period number 6. Atomic number 70 comes in this category, period number 6. And you can easily check which one is your lengthenide, which one is your actinide. Similarly, my dear students, if the atomic number of the element neither is in this category nor is in this category, if the atomic number of the element does not belong to this category, does not belong to this category, so what do we have to do? And remember, period number is equal. Period number is equal to period number of the next inert gas. If the atomic number of the element neither comes in first category nor in second category, then remember, period number of the element is nothing but it is the period number of next inert gas. What does that mean? First of all, these are your inert gases. Helium, neon, argon, krypton, xenon, radon. These are your inert gases, right? First of all, the period number of helium is, the atomic number of helium is 2, right? Atomic number of neon is 10. Atomic number of argon is 18. So basically, you know this magic number, 2, 8, 8, 2, 8, 8, 18, 18, 32. So what you have to do is, have a look. 2 plus 8 comes out to be 10. 10 plus 8 comes out to be 18. 18 plus 18, 36. 36 plus 18, 54. 54 plus 32, 86. Right? So this is the magic number which I believe every one of you would have heard. 2, 8, 8, 18, 18, 32. So I would say atomic number of helium is 2. Atomic number of neon is 10. Argon is 18. Krypton is 36. Xenon is 54. Radon is 86. These are the atomic number of these noble gases. And helium belongs to your first group. Neon, second group element. Third group element. Fourth group. Sorry, I'm talking about the period. Helium belongs to first period. Neon belongs to second period. Argon is the third period element. Krypton, fourth period element. Xenon, fifth period element. Radon, sixth period element. Now what you have to understand here. For example, I've got the element whose atomic number is 44. Let's say I've got the element whose atomic number is 44. Can you quickly tell me The element whose atomic number 44, is it coming into this category? No. Is it coming into this category? No. So this element neither comes in this category nor in this category. So what would be its period number? Its period number will be equal to the period number of next inert gas. Next inert gas. So after 44, after atomic number 44, what is the atomic number of next inert gas? After 44, the atomic number of next inert gas is this. That is 54. Perfect. And this particular element has got the period number 5. So I would say this will also have period number 5. Got it? Perfect. Similarly, if the atomic number of the element is 32, 32 neither comes in this category nor comes in this category. So after 32, which one? After atomic number 32, what is the next inert gas atomic number? After 32, 36 comes, right? So this is the atomic number of the next inert gas. And this next inert gas, it has got the period number 4. So I would say this particular element also will have period number 4. I believe this particular point is clear, right? I believe this particular point is clear. And if this is clear, my dear student, if this is clear, let's move on to a few more things. What is that? That is identification of the group. Right now, I was talking about the identification of period. Now, let's talk about the identification of the group. Understand properly what I'll be saying. If atomic number is between this or this, if the atomic number is between this or this, I told you they are your F-block elements, right? And F-block elements, they are all in group 3. That I told you a few minutes back on. Now, if the atomic number is between 104 to 118, if the atomic number comes in this category, then group number is equal to last 2 digits. Group number is equal to last 2 digits. For example, I've got the element whose atomic number is 108, and I'm asking about the group number. What is the group number of this element? Since 108 comes in this category, 108 comes in this category, and if you look at the last 2 digits, that is 8, so element belongs to group number 8, right? For example, I've got the element whose atomic number is 116. I want to know its group number. Now, 116 comes in this category, so I would say last 2 digits is equal to 16, so group number of the element is nothing but 16. Perfect? Now, similarly, my dear students, similarly, just a second. Now, the next point. If the atomic number of the element, neither comes in this category, nor in this category, nor in this category. If the atomic number of the element neither comes in this category, nor in this, nor in this, how do we get the group number at that time? The formula is 18 minus atomic number of next inert gas, right? Minus atomic number of the element. What does that mean? For example, I'm taking an element whose atomic number is 44. 44 neither comes in this category, nor in this, nor in this. So how do I calculate its group number? Its group number will be equal to 18 minus next inert gas. After 44, the next inert gas atomic number is 54. So it's going to be 54. 54 minus Z. What is the Z value for this element? That is 44. So the value comes out to be 54 minus 44 is 10. 18 minus 10 is 8. I would say group number of this element comes out to be 8. Perfect. My dear students, remember one more thing. When you use this formula, after using this formula, if the answer comes out to be negative, then use this particular formula. 32 minus next inert gas atomic number minus atomic number of the element. For example, I've got the element whose atomic number is 32. 32 neither is in this category, nor in this, anywhere, right? So I'll first try to use this particular formula. Group number is equal 18 minus, what is the next inert gas after 32? After 32, next inert gas has the atomic number of 36. So it's going to be 36 minus, atomic number is how much? Atomic number is 32. Right? So you can easily get it. How much is it going to be? Quick. 32 minus 36 minus 32 is 4. 18 minus 4 is 14. So group number of this particular element is 14 over. And again, I'm telling you, when you use this particular formula, if the answer comes out to be negative, then replace 18 with 32 here. That's all you have to do. So this is how you can get the period number or group number of the element if either atomic number is given or the electronic configuration is given. Can you let me know once in the chats if all these things are clear to everyone? Quickly in the chats, people, everyone in the chats. So one short question will be asked from this. Short question. Everyone in the chats, people, quick. Why is it so complicated? It's not complicated. You just go through it once again at home. After writing the notes, it'll be easy for you. All clear? Let me know once in the chats, quick. Quick, people, everyone. Someone is asking about the duration. Duration is going to be 5 hours, as I told you already. Class 12th Inorganic will be taken on Tuesday, after 2 days. Yes, JEE students can also listen to this. Chalo, let's move on to one more thing, guys. What is that? This is something which you all love. What is that? Naming of the elements with atomic number greater than 100. Naming of the element with atomic number greater than 100. This is something which everyone loves. Yeah? So, for the number 0, the prefix used is nil. For the number 1, prefix used is un. For number 2, prefix used is pi. For number 3, tri, quad, pent, hex, sept, oct, n. 9 is en and n. Okay? Right? And the suffix used is ium. Suffix used is ium. This is something which I believe every one of you would be already knowing. For example, I've got the element with atomic number 103. 103. Right? I want to know its name. 1 means the prefix used is un. Right? 0 is nil. Right? 3 is tri. And at the end, I have to use ium. Right? This is the name of it. And what would be this symbol? Its symbol will be un starts with u, nil starts with n, and tri starts with t. UNT is going to be its symbol. For example, I've got the element with atomic number 117, for example. I've got the element with atomic number 117, right? 1 means, again, un. 1 means un. This one again means un, right? 7 means sept. Sept. And at the end, I have to use the suffix as ium. So what is going to be the symbol of this particular element? Un starts with u, un starts with u, and sept starts with s. So UUS is going to be the symbol of this element. This is, I believe, everyone would be already knowing, right? So I'm not going to waste a lot of time in this because it's pretty much simple. Can you tell me in the chats what is the name of this particular one? 107. What is the name of this particular element whose atomic number is 107? I want to know in the chats, quick. Quickly in the chats. Every one of you. Quickly, guys. Perfect. So this is un, this is nil, this is sept, and at the end, I'll be using IUM. So un, nil, septium. Un, nil, septium is going to be the IUPAC, name of the element whose atomic number is 107. Okay. So I believe this particular part is clear. And if this particular part is clear, there is a topic, one important topic, my dear students, which you should know. What is that? That is shielding effect. That is shielding effect. Okay. What is shielding or screening effect? How do we exactly define it? How do we exactly define it? As I told you, I've already made the things written on the screen already, so our time will be minimized. The duration of the session will be less. So let's talk about the shielding effect. Let's talk about the screening effect. Let's try to understand. My dear students, if you read the definition first, the definition says the decrease in the force of attraction, on the valence electron due to the inertial electrons. The decrease in the force of attraction on the valence electron due to the inertial electrons is what you call a screening effect or shielding effect. Let's try to understand this. My dear students, for example, this is the nucleus of the atom. Let's say I have got the atom whose nucleus is this. And this is the electron which is present in the last shell. This is the electron which is present in the last shell, and this electron is revolving around the nucleus. Imagine there are no other electrons in between nucleus and electron. Imagine between these two, there are no other electrons. There are no other electrons. Let's imagine that. Since I would say this nucleus has positive charge, electron has negative charge. So can I say nucleus will be attracting this electron with some force? Nucleus will be attracting this electron with some force. Let that force be 5 Newton. For example, nucleus right now is attracting this electron with a force of 5 Newton. Just to make you understand. Just to make you understand. Okay. Now, for example, I have the nucleus here. The same nucleus I have, right? And this is the last electron. This is the last electron. This is the last electron, which I'm calling as test electron. Now, my dear students, let's say there are some inner shells as well, which contains some more electrons. There are some inner shells as well, which contain some more electrons. Now, if I consider this particular electron, how many forces will be experienced by this electron? The first force, this nucleus will try to attract this electron towards itself. That is the first force. The second force, these electrons, these inner shell electrons will be repelling this electron. These inner shell electrons will be repelling this electron. These inner shell electrons will be repelling this electron. Now tell me the net force experienced by the electron. If the net force experienced by the electron, the net force of attraction experienced by the electron due to nucleus right now, is it going to be 5 Newton or less than that? You tell me. The net force experienced by this electron right now in this particular scenario, is it going to be 5 Newton or less than that? It will be less than that, right? Let the force of attraction experienced by this electron right now, net force of attraction experienced by this electron right now due to nucleus is 3 Newton. Is 3 Newton, right? Perfect. Why it happened? Because of these repulsions. Perfect. So earlier the same electron was experiencing 5 Newton force by the nucleus. Now the same electron is experiencing 3 Newton force by the nucleus. So has the force of attraction on the valence electron increased or decreased? I would say force of attraction on the valence electron has decreased because of the presence of the inertial electrons. And this decrease in the force of attraction, on the valence shell due to the inertial electrons, this decrease in the force of attraction is what you call as the screening effect or shielding effect, right? So I would say it in simple words. I would say these inner shell electrons, they are creating a shield over here. They are creating a shield due to which the force of attraction experienced by this electron will be less than expected. As simple as that. Okay? Perfect. Perfect, guys. Now, there are two things which we are aware. One is called as effective shielding. One is called as ineffective shielding. When it comes to effective shielding, proper shielding, good shielding, effective shielding, due to more shielding by the inner electrons, force experienced by the outer electron will be less. And if the force experienced by the outer electron is less, I would say effective nuclear charge is less. Okay? So remember, due to good shielding, due to effective shielding, the force of attraction experienced by the outermost electron will be less. That means effective nuclear charge will be less. Perfect? Similarly, due to ineffective shielding, due to ineffective shielding, if these electrons are not doing proper shielding, the force of attraction experienced by the last electron will be more. That means effective nuclear charge will be more. These are the two things which I would want every one of you to remember. Number one, due to effective shielding, effective nuclear charge will be less. Due to ineffective shielding, effective nuclear charge will be more. Okay? Two things which I would want every one of you to remember. Now, my dear students, you have got your s orbitals, p orbitals, d orbitals, and f orbitals. Remember, this is basically the shielding order. S orbital does maximum shielding, effective shielding because it's closer to the nucleus. Your d and f, they do not do the effective shielding, they do ineffective shielding. This is the order which I believe every one of you would have studied till now. Now you just have to remember your S S orbitals, they do the maximum shielding, they do the effective shielding. Your D and F orbitals, they do ineffective shielding. They do not do the proper shielding over here, right? So this is the order of the shielding effect which you have to remember. And my dear students, if you remember these two things, then there is something which I want to share with all of you. What is that? Let's try to understand. My dear students, for example, you have got the atom A. You have got the atom A. Let this atom has some 7 electrons. And let this atom has got some 7 protons. Right? This atom A, it has got 7 electrons, it has got 7 protons. I would say right now, these 7 electrons are holding these 7 protons are holding these 7 electrons. I would say right now, these 7 protons are holding what? 7 protons are holding 7 electrons. Right? 7 protons are holding 7 electrons. Now, for example, if I take 1 electron out, from A, it becomes A positive. It becomes A positive. So how many electrons will be there now? 6. Protons are still going to be same, 7. So earlier, 7 protons were holding 7 electrons. Now the same 7 protons are holding 6 electrons only. Can I say force of attraction experienced by the outermost electron here will be more? And if the force of attraction experienced by the outermost electron here is more, what does that mean? That means effective nuclear charge is more. Perfect. Here I would say comparatively effective nuclear charge is less. So my point is, when the parent atom gets converted into its cation, what happens to effective nuclear charge? Effective nuclear charge increases. And I would say effective nuclear charge is directly proportional to positive charge. Effective nuclear charge is directly proportional to positive charge. More the positive charge, more the effective nuclear charge. Similarly, my dear students, effective nuclear charge is inversely proportional to negative charge. Effective nuclear charge is inversely proportional to negative charge. This is one very, very, very important statement which I would want every one of you to remember from now on. Okay? Perfectly done. And my dear students, if this is perfectly done, then there is a time to do few questions. Okay, one question I'm giving you. Tell me the answer of this one. In sodium atom, the screening of 3s electron is due to. What do you think about this? I believe everyone should easily answer this question. In sodium, the screening of 3s electron is due to what? First of all, if you talk about your sodium, what is the outermost configuration of sodium? 1s2, 2s2, 2p6, and 3s1. So shielding, the screening of 3s is due to the presence of inertial electrons. Inertial electrons are this: 1s2, 2s2, 2p6. So it's going to be option C. That is the correct answer of this particular question. Simple and basic. Yeah? Perfect? Yes, it is perfect. Now, my dear students, there is one more topic from which questions are asked. What is that? Questions based on atomic radius. Questions based on atomic size. Okay? Questions based on atomic radius. Questions based on atomic size. First of all, there are few points which I would want you guys to remember. Because they are very important. What are those points? My dear students, what is first of all atomic radius? In simple words, I'll define atomic radius as the distance between the nucleus and the outermost shell. The distance between the nucleus and the outermost shell in an isolated atom. That means that atom which has not formed the bond. The atom which is in non-bonded form, the atom which has not formed the bond yet, we call that as the isolated atom. So in case of the isolated atom, the distance from the nucleus to the outermost shell is what you call as atomic radius. Okay. Now, my dear students, this atomic radius, it cannot be measured experimentally. There are different logics which you can give to that. The first logic is you won't get the atom in the isolated form. Number one. Number two, the boundary of the atom is not defined. Right? So you cannot technically measure the atomic radius of the atom. Now, I would say since atom exists in bonded state, atom, you would always say atom you'll see existing in bonded state, right? And if the atom is in bonded state, that means atomic radius is also defined under which conditions? Atomic radius is also defined under bonded conditions. Atomic radius is also defined under bonded conditions. Why? Because atoms, you won't find isolated. You won't find them in isolated form. They'll be always in bonded form, right? Therefore, atomic radius is also defined under bonded conditions. One is called as covalent radius, one is called as metallic radius, one is called as van der Waals radius, right? So in case of covalent radius, covalent radius is defined when the atoms would have formed a covalent bond, when the atoms would have formed the metallic bond, when the atoms or molecules are attracted towards each other by the help of van der Waals force of attraction. And you just have to remember one statement, just one statement. Van der Waals radius is more than that of metallic radius, and metallic radius is more than that of covalent radius. This is just the thing which you have to remember. When you have to give the order of the covalent radius, metallic radius, and van der Waals radius. This is the only point which you have to remember over here. What is that? Van der Waals radius will be more than that of metallic radius, and metallic radius will be more than that of covalent radius. This is the question which can be asked here. Number one. Number two, my dear students. What is that? Have you heard about isoelectronic species? What are isoelectronic species, if I ask you? What are isoelectronic species? Isoelectronic species are the ones which have got same number of electrons. My dear students, whenever you have to give the order of the atomic radii, in case of isoelectronic species, isoelectronic species are the ones which have got same number of electrons. Now remember, few minutes back I told you, your effective nuclear charge is directly proportional to positive charge, inversely proportional to negative charge. Something I told you a few minutes back, right? That means more the positive charge on the species, more is the effective nuclear charge. More effective nuclear charge means more is the attraction between the nucleus and the outermost electron. If more is the attraction between nucleus and the outermost electron, that means outermost electron would have come closer. That means the size would have decreased, right? Can I say more the positive charge, more the effective nuclear charge, lesser the size? So atomic radius, will it be directly proportional to effective or inversely? It will be inversely proportional to effective nuclear charge. Atomic radius is inversely proportional to effective nuclear charge. And you know effective nuclear charge, it's directly proportional to positive charge, inversely proportional to negative charge. So this is the order which you have to remember. Okay? For example, all of these are your isoelectronic species. They have got same number of electrons. Now you have to give the order of size. In short, more the negative charge, more the size. More the negative charge, more the size. More the positive charge, lesser the size. So this is the order. This has got more negative charge, more size. Right? This is the order of these this is the order of the size of these isoelectrons. As simple as that. Okay? Perfect, guys. Perfect. I believe this is clear. And if this is clear, people, if this is clear, there is one more thing which I would want to talk about. What is that? What happens to atomic radius along the period? My dear students, along the period, what happens to effective nuclear charge? Along the period, effective nuclear charge increases. And as I told you, atomic radius is inversely proportional to effective nuclear charge. So along the period, if Z effective increases, that means size decreases. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, size is going to decrease. Along the period, right? Am I clear with this? Now, my dear students, remember, after fluorine, what comes? Oxygen, fluorine, neon. So fluorine, neon. So technically, I would say neon should have least size in the period. But neon does not have the least size in the period. Neon does not have lesser size than that of fluorine. Neon has got more size than that of fluorine. What is the logic? Because in case of neon, Neon, noble gas. In case of noble gases, there are van der Waals attractions. So van der Waals radius is defined for neon, and van der Waals radius is more than that of metallic. Metallic is more than that of covalent. So because of that, I would say neon has got more size than that of fluorine, because neon forms which kind of interaction? It forms the van der Waals interaction. Okay. Now, guys, if you talk about a size along the group, down the group. Now, you know, down the group, what happens to size? See, down the group, shell number increases. Down the group, shell number increases. And if shell number increases, automatically size is increasing, right? So atomic radius is directly proportional to number of shells. Down the group, number of shells increase. Down the group in the periodic table, number of shells increase. And if number of shells are increasing, that means size is automatically going to increase. So lithium, sodium, potassium, rubidium, cesium. Cesium will have maximum size, followed by rubidium, potassium, sodium, lithium. Okay? Now, similarly, guys, similarly, when you talk about your transition elements, for example, I talk about your 3D series. In case of 3D series, what all elements do you have? Cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay? This is your 3D series. Now, in 3D series, you just have to remember few things. What are those few things? Try to understand. My dear students, from scandium to iron, what happens? What happens? Size decrease. From scandium to iron, size decreases. Reason? Because effective nuclear charge dominates over screening. Effective nuclear charge dominates over screening. Effective nuclear charge dominates over screening. And effective nuclear charge, if it is dominating, size will automatically decrease. Right? So from scandium to iron. Then in iron, cobalt, nickel, the size is almost the same. The size is almost the same. Because effective nuclear charge and screening, they counterbalance each. Size is almost the same in iron, cobalt, nickel. Then in case of copper to zinc, in case of this, screening dominates over Z effective, due to which size increase. So this is one order, my dear students, which I would want you guys to remember from now on. Okay? This is the order in case of 3D. This is the order in case of 3D. Now, similarly, there is one more thing which I would want to tell you here. That's also important, I feel. Since in case of D block elements, you have got 3D series, 4D series, 5D series. Now, down the group, what happens to shell number? Shell number increases. If you go down the group, shell number increases, so size should increase. So if you talk about these three elements, SCYLA, size will increase for sure. Down the group, size increases. The order of size will be LA will have maximum size, followed by Y, followed by SC. Okay? I'm talking about this particular group. But talk about all the other groups. For example, you have got titanium, zirconium, hafnium. Right? Down the group, what should happen to the size? Size should increase. So what should be the expected order? I should say hafnium should have more size than that of zirconium. Zirconium should have more size than that of titanium. This is the expected order. But my dear students, zirconium has more size than titanium. But zirconium and hafnium, they have got almost same size. Why is that? What is the logic? See, before hafnium, there comes F block elements. And in case of F block elements, my dear students, the last electron will be in F subshell. And F subshell has got poor screening, ineffective shielding. Due to ineffective shielding, Z effective increases. And if Z effective increases, size decreases. So one of the factor, from zirconium to hafnium, shell number is increasing, size should increase. From zirconium to hafnium, due to ineffective shielding of F block elements, Z effective increase, size should decrease. So one factor is telling you size should increase, one factor is telling you size should decrease. So it remains almost the same. They are counterbalanced. You call it as the lanthanoid contraction as well. Yes? Perfect. Same goes here. VNBTA. What happens? Technically, size should increase, but these two will have almost similar. These two will have almost similar size. These two will have similar. These two will have similar. The reason is because of the ineffective shielding of the F electrons. Yeah? I believe you are going to remember this as well. And if you are remembering this, then tell me, what do you think will be the answer of this particular question? Question was asked in your NEET 2018. I want everyone to let me know the answer of this question. Quick. Quickly, people. Everyone. See, your boron, gallium, aluminium, indium, thallium, they are your group 13 elements. Boron, aluminium, gallium, indium, and thallium. They are your group 13 elements. So technically, what should happen to the size? Down the group, I would say size should increase. Size should increase. So what should be the expected order? Expected order is something like this. Boron should have less size, followed by aluminium, followed by gallium, followed by indium, followed by thallium. This is the expected order. This is the expected order. But is it going to be the actual order? This is not the actual order. Why is that? Why is that? There's a logic. My dear students, before gallium, there are your D block elements. There are your D block elements. And in case of D block elements, before gallium, you'll find D block elements. In case of D block elements, the last electron enters into D subshell. And D orbitals, they show pore shielding. And if they show pore shielding, effective nuclear charge increases, size decreases. So that is the reason why gallium has lesser size than that of aluminium. So the order is boron, then comes gallium, then comes aluminium, then comes indium, then comes thallium. This is the actual order. This is the actual order. Okay? This is the actual order. I believe it's clear. Okay? Boron, gallium, aluminium, indium, thallium. Remember it. Tell me the answer of this particular question. Oh, I have already marked the answer here. You have to give the order of their size. You have to give the order of their size. These are isoelectronic species. More the positive charge, lesser the size. Simple. In case of isoelectronic species. More the positive charge, lesser the size. More the positive charge, lesser. So this is the answer. More the negative charge, more the size. More the positive charge, lesser the size. Few things which I discussed already with all of you. Identify the wrong statement in the following. Amongst isoelectronic species, smaller the positive charge on the cation, smaller the positive charge on the cation, larger will be the size. Is that? You have to identify the incorrect statement. The incorrect statement is this one. Do you understand why? Since we know size is inversely proportional to what? Positive charge. So more positive charge means lesser size. Here they are saying smaller the positive charge, smaller will be the size. Is that right? Size and positive charge, they are inversely proportional. So lesser the positive charge, more should be this. This is the incorrect one. All right, people. Am I clear? Now, again, questions have been repeated on isoelectronic species, their size. This is something which all of you can easily check now, right? You know, more the negative charge, more the size. So S di negative has got more negative charge, more the negative charge, more the size. So it's definitely option number C. There's nothing to think over here. Similarly, you can give the order of this one as well. You can give the order of this one as well. Okay. You can give the, again, these are your isoelectronic species, and you know, more the positive charge, lesser is going to be the size. More the positive charge, lesser is going to be the size, right? You know that already. Perfect. You can give the order easily. So order of this particular question is going to be C. Correct? Right, people? Because more the positive charge, lesser is going to be this. You know it already. Now comes one more term. What is that? That's ionization energy. Again, important, and questions have been asked from this. What is ionization energy? How do we define ionization energy? How do we define ionization energy? Sir, P block, sir, P block, sir, P block. P block will be done on Tuesday. Okay? With your class 12th inorganic marathon. Okay? Now don't ask me the same question again. Clear, guys? I think all the things are clear till here. I believe so. If yes, give me some thumbs ups in the chat so that I'll get to know I'm perfectly clear till here. Till now. Quickly in the chats. This session is enough. Quickly in the chats, people. All right, people. Perfect. So let's move on to ionization enthalpy. What is your ionization enthalpy? What is your ionization energy? My dear students, let's exactly have a look on the definition first, then I'll make you understand what this ionization energy is all about. Okay? Let's have a look. See guys, ionization energy is nothing but it is the minimum amount of energy. Minimum amount of energy. Minimum amount of energy which is required to remove the most loosely bonded outermost shell electron. The minimum amount of energy which is required to remove the most loosely bound outermost electron in the ground state of an isolated gaseous atom. Now, what does that mean? What does that mean? Let's try to understand what exactly it means. For example, my dear students, let's say I've got the atom whose nucleus is this. Whose nucleus is this? Let's say this is shell, this is inner shell, this is also one shell, and this is the outermost shell. This is the outermost shell. All these inner shells, they are containing the electron. All these inner shells are containing the electron. And this outermost shell, for example, it has got the electron here. I'm calling this as the outermost electron. Now, you know, the outermost electron is the most loosely bonded electron. See, nucleus will be attracting all these electrons towards itself. Now, this electron is far from the nucleus. It will experience less force of attraction. So I would say this electron is the most loosely bonded electron here. It is the most loosely bonded electron here because it is far from the nucleus. It is far from the nucleus. Now, imagine this atom is an isolated gaseous state. It is an isolated gaseous form. This atom is an isolated gaseous state. Perfect. Now, my dear students, I would say this nucleus, it will be holding this electron towards itself. There will be force of attraction between nucleus and this outermost electron. Now, if you want to remove this outermost electron, if you want to make sure the electron comes out of the influence of the nucleus, if you want to make sure this most loosely bonded electron, it comes out of the influence of the nucleus. What you have to do? If you want this electron to be removed, right? If you want this electron to be out of the influence of the nucleus, you have to break this attraction. And in order to break the attraction, energy is required. In order to break the attraction, energy is required. Now, let me tell you the minimum amount of energy which is required to remove the most loosely bonded electron from the isolated gaseous atom. That minimum amount of energy required is what you call as the ionization energy. So ionization energy is nothing but it is the minimum amount of energy which is required to remove the most loosely bonded electron from the isolated gaseous atom. Okay. For example, this is the isolated gaseous atom M. This is the isolated gaseous atom M. If you are providing it the ionization energy, providing the ionization energy meaning, what does that mean? That means you are providing the minimum amount of energy which is enough to knock out, to remove the outermost electron. So you are removing outermost electron from M. So therefore M gets converted into what? M positive. And with that you got one electron as well. Right? And the amount of energy required in this particular process is what you call as ionization energy. Pretty much simple. Now, my dear students, one important thing. What is that? For example, you have got the isolated gaseous atom A. You are taking one electron out from here. It gets converted into A positive. The amount of energy required to take the electron out is called as first ionization energy. Now, since you have A positive here, now if you want to take electron out from A positive, it gets converted into A di positive, right? The amount of energy required in this particular case is called as ionization energy 2. Now, if you want to take one more electron out from A di positive, right? The amount of energy required in this particular case is ionization energy. And remember the order, ionization energy 3 will be always greater than that of ionization energy 2, which will be always greater than that of ionization energy 1. Remember this particular case, my dear student, right? Ionization energy 3 is greater than that of ionization energy 2, is greater than that of ionization energy 1. First ionization energy means, that means you are taking the first electron out from A. Second ionization energy meaning, that means you are taking the electron out from A positive. Third ionization energy, that means you are taking the electron out from A di positive. Okay? Remember this particular order, it is frequently asked. Now, people, what are the factors which affect this ionization energy? What are the factors which affect this ionization energy? Think over it, my dear students. Just tell me one thing. If the effective nuclear charge is more, think over it. If the effective nuclear charge is more, that means force of attraction between nucleus and the outermost electron is more. And if the force of attraction between nucleus and outermost electron is more, that means more amount of energy is required to take that electron out. Means more is the ionization energy. Simple. Right? Perfect. So I would say ionization energy and effective nuclear charge, are they directly proportional or inversely? They are directly proportional. More the effective nuclear charge, more is the force of attraction between nucleus and the outermost electron. More energy is required to take that electron out. More is the ionization energy in short. So remember, ionization energy is directly proportional to effective nuclear charge. And you know, effective nuclear charge is itself directly proportional to positive charge, inversely proportional to negative charge. We have discussed that. Now we can give the order of the ionization energies of these. What is the order of ionization energy? Fe tri positive, more positive charge, more effective nuclear charge, more ionization energy. Then that of Fe di positive, then that of Fe. Okay? These sort of questions you can easily solve from now on. Number one. Number two, my dear students, number two. You know the half-filled configurations or fully filled configurations. Half-filled configurations or fully filled configurations. Half-filled are P3 configuration, D5, F7. These are exactly half-filled configurations. These are fully filled configurations. Half-filled configurations, fully filled configurations, they are more stable. So to take electron out from them, more energy will be required. More energy will be required. Therefore, I would talk about one simple thing. Compare the ionization energy of nitrogen and oxygen. Here the outermost configuration is 2p3. Here the outermost configuration is 2p4. It is half-filled, more stable. To take electron out from nitrogen, to take outermost electron out from nitrogen, more energy is required. That is the reason why nitrogen has got more ionization energy than that of oxygen. I'm talking about the first ionization energy. Right? Now, if I want to compare the second ionization energy of nitrogen and oxygen, if I want to compare the second ionization energy of nitrogen and oxygen, my dear students, if I want to compare the second ionization energy of nitrogen and oxygen, what do we have to do? If I talk about second ionization energy, that means the electron has to be taken out from 2p2 configuration now. The electron has to be taken out from 2p3 configuration now. Which one is more stable? This configuration is more stable. So more energy is required in this particular case. So second ionization energy of oxygen will be more than that of nitrogen. Remember this particular case as well. Okay, this is again important. All right. Now, let's talk about certain orders now. My dear students, along the period, what happens? On moving from left to right in the period, effective nuclear charge increases. So, it becomes difficult to remove the outermost electron. That means more energy is required, more will be the ionization energy. So, technically, I would say, what exactly? Technically, I would say, on moving from left to right across the period, ionization energy generally increases. Okay? Ionization energy generally increases. So, if you look at these second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So, what is the expected order? Expected order is like this: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Right? Neon. So, expected order is on moving from left to right, ionization energy should increase. So, this is the expected order of ionization energy. This is the expected order of ionization energy. What would be the actual order of ionization energy? This is the expected one. But this is not the actual one. What is the actual one? Understand. The outermost electron in beryllium is in 2s2. Right? Boron, its outermost configuration is 2p1. So this 2s2. It's completely filled. Right? 2p1. Partially filled. Completely filled. Partially filled. Completely filled means more stable. More stable means more energy required. That is the reason beryllium has got more ionization energy than that of boron. Similarly, this oxygen and nitrogen we have already discussed. Nitrogen has got more ionization energy than that of oxygen. This is the actual order. Okay, this question is frequently asked. So remember that. Am I clear till here? Am I clear till here, people? Now, one thing which you already know, down the group, what happens to size? Size increases. If down the group size increases, that means force of attraction between nucleus and outermost electron, that decreases. Size increases. Force of attraction between nucleus and outermost electron decreases. That means less energy is required to remove the outermost electron. Less will be the ionization energy. Technically, I would say down the group ionization energy decreases. Down the group ionization energy decreases. Okay, so remember this particular point as well, and I believe it's perfectly clear to you. Now, my dear students, you can talk about the metallic character as well in terms of ionization energy. You can talk about metallic character as well in terms of ionization energy. I just want you to think under these parameters. What exactly? You know, if I talk about metals have got the tendency to lose electrons. Metals have the tendency to do what? Metals have got the tendency to lose electrons. Okay? Metals have the tendency to lose electrons. I would say that metal which has got lesser ionization energy, that metal which has got lesser ionization energy, would lose the electron easily. And when the metal loses the electron easily, that means more is the reactivity of the metal. Okay? More is the reactivity of the metal. Understood, people? Is this particular point clear? Is this point clear? So remember, your metallic character is inversely proportional to ionization energy. Okay? Lesser the ionization energy. That means lesser energy is required to take the electron out. So the metal has more tendency to lose electron, I would say. And more the tendency of the metal to lose electron, more is the metallic character, in short. So in short, metallic character is inversely proportional to ionization energy. Okay? Right? Same is the order for reactivity of metals. Right? Lesser the ionization energy, more easily electron will be lost by the metal. Right? And the tendency to lose the electrons defines the reactivity of the metal. Right? So more will be the reactivity of the metal. This is something which you can directly remember. Now, my dear students, one more important application of ionization energy. What is that? Understand properly what I'm going to say. Remember this. Okay? Remember this. With the help of ionization energies, we can talk about the stability of oxidation states of the element. For example, my dear students, I've got sodium. Okay? I'm taking the outermost electron out by supplying ionization energy 1. I'm taking one more electron out. It gets converted into Na positive by supplying ionization energy 2. So ionization energy 1, ionization energy 2. These are called as successive ionization energy. This oxidation state of sodium here is +1. Oxidation state of sodium here is +2. +1 is what I call as lowest oxidation state. +2 I call as highest oxidation. +1 I call as lowest oxidation state. +2 I call as highest oxidation state. Now, guys, understand what exactly I'm trying to say. And what exactly I want you guys to remember. See, my dear students, if the difference between two successive ionization energies, of an element is greater or equal to 16 volts, electron volts, then remember the lower oxidation state is more stable. This is the question asked. They'll give you the successive ionization energies of an element, and they'll ask you which oxidation state is more stable, higher or lower. Remember, in short, if the difference between the successive ionization energies of an element is greater or equal to 16 electron volts, then the lower oxidation state is more stable, right? And let me tell you, in case of sodium, the difference between the successive ionization energies is 42.7, which is greater than 16 electron volts. That means lower oxidation state will be more stable. That means +1 of sodium will be more stable than that of +2. I would say Na positive is more stable than Na di positive. Okay? This is the thing which I would want every one of you to remember. Okay, guys? All right, all right. Similarly, guys, there is one more point. There is one more point. If the difference between successive ionization energies of an element is less or equal to 11 electron volt, is less or equal to 11 electron volt, then remember, higher oxidation state is more stable. Higher oxidation state is more stable. For example, talk about magnesium. Okay, take 1 electron out from magnesium, it gets converted into Mg positive, and the energy required is called as ionization energy 1. Take 1 more electron out from here, energy required is ionization energy 2. And let me tell you, the difference between these successive ionization energies is equal to 7.4 electron volt. 7.4 electron volt is less than 11 electron volt. That means highest oxidation state is more stable. Now, lowest oxidation state of manganese is +1 here, highest is +2. So Mg di positive will be more stable in this particular case. Mg di positive will be more stable in this particular case. Remember this particular point from this question will be asked. Now, the third thing which is easily asked in your examination, what is that? My dear students, for example, you have got an element whose first ionization energy is 3 volt, second ionization energy is 10, third is 20, fourth is 200. Fourth is 200 electron volt. Now, do you see massive jump from 20 to 200? Massive jump from 20 to 200. And they are asking me how many valence electrons the atom has. See, if I think logically, let's say this is the outermost shell, this is the inner shell, this is the nucleus here. Perfect. So to take the first electron out, how much energy is required? 3 electron volt. Not much. To take the second electron out, 10 electron volt is required, right? To take the third electron out, 20 electron volt is required. Now to take the fourth electron out, 200 electron volt is required. Jump is massive. That means the next electron would be taken out from the inner shell. That's why more energy is required here. Perfect. Because the distance between this and nucleus is less, force of attraction will be more. That's why more energy is required in order to take this electron out. So that means how many valence electrons do we have? 3 valence electrons. So these sort of questions are asked in your examination. You should be able to solve these questions. Did you understand this particular concept? Okay, guys? Can you let me know once in the chats if this is clear? Can you tell me once in the chats if this is clear? I'll give you a question on this in some time. I'll give you a question. Okay, let's solve the question. Let's solve the question. Tell me the answer of this question. Similar type. Similar type, people. Similar type of question. See, the first ionization potential, the first ionization energy is 7.1, second is 14, third is 34, this is 46, then comes 162. The jump is massive here. So it means to take the first electron out, this much energy is required. To take the second electron out, this much energy is required. To take the third electron out, this much energy. To take the fourth electron out, this much electron is required. Now, to take the fifth electron out, a lot of energy is required. It means these 4 electrons would be present in the last shell. And this fifth electron, which I was supposed to take out here, it would be present in the inner shell. So, the last shell has got 4 electrons. So, I would say the atom has got 4 valence electrons. Which atom has got 4 valence electrons? It's silicon. Carbon silicon. Silicon has got 4 valence electrons. Right? Isn't it clear, guys? Isn't it clear? Break I'll give you after completing this chapter, and this chapter will take 20 more minutes to complete. That's it. Okay? Now, my dear students, there is something called as electron affinity. There is something called as electron affinity. Again, the simple topic, right? Few things you are supposed to remember, and that's it. What is electron affinity basically? I'm not going into the details of electron affinity. I'll tell you some things which you are supposed to remember so that you can solve the question. My dear students, the amount of energy released, it is the amount of energy released when an electron is added to the valence shell of an isolated gaseous atom. This is, for example, an isolated gaseous atom. It is an isolated gaseous atom. And you are giving it 1 electron. When you are giving it 1 electron, it's getting converted into X negative. Right? It's getting converted into X negative. The amount of energy released during this particular process is what you call as electron affinity. Electron affinity is nothing. It is the amount of energy released when an extra electron is given to the isolated gaseous atom. Right? And the amount of energy released is what you call as electron affinity. Okay? It is what you call as electron affinity. It is what you call as electron affinity. And my dear students, one more thing. For example, you have got the isolated gaseous atom X. You are giving 1 electron to it. It got converted into X negative gas. The amount of energy released in this particular process is called as electron affinity 1. Now we have got X negative. You are giving it 1 more electron. So that it gets converted into X di negative. The amount of energy. See, the first ionization energy is generally, it is always exothermic. That means energy is released. The second ionization energy is always endothermic. It is always endothermic. The first ionization energy is always exothermic, except when it comes to the stable configurations that I'll talk about in some time. Right? But remember, when you give the electron, when you talk about the second electron affinity, it's always endothermic. Perfect. Similarly, if you talk about third electron affinity, that means X di negative gas, you are giving 1 more electron to it, and it gets converted into X tri negative gas, right? And the amount of energy absorbed in this particular case is going to be electron affinity 3. Now, few things which you have to remember. What is that? Generally, first electron addition of an isolated gaseous atom is an exothermic process, except stable configurations, like your nitrogen. It has got stable configuration. So if you give 1 electron to nitrogen, right, it won't try to accept it. Basically. Okay. So this is something which I already made you understand. Only one thing which you have to remember: the first ionization energy is generally exothermic, and if you talk about the second ionization energy, the second electron addition of the isolated gaseous atom is always endothermic process, right? Due to the repulsions here. Because this is negative, electron is negative, there will be repulsions. So this particular process, the second electron affinity will be, you'll find it endothermic. Okay. Now, my dear students, what are the factors? What are the factors on which this electron gain enthalpy depends upon? It is pretty much simple. What is that? My dear students, lesser the size of the atom. For example, this is one of the atoms whose size is this much. This is one of the atoms whose size is this much. Perfect. This is the electron which wants to be added here. This is the nucleus. Right? This is the electron which wants to be added. This is the electron which wants to be added. Now, the distance between nucleus and this electron is less. Force of attraction is more. The force of attraction between these two is less. Here, the force of attraction is more. Right? So, this electron, this atom has got more tendency to get this incoming electron. Right? So, I would say electron affinity in this particular case would be more. electron affinity, the affinity towards the electron will be more in this particular case because size is less, the distance is less, force of attraction is more. So remember, electron affinity is inversely proportional to atomic size. Lesser the size, more the electron affinity. In short. Similarly, this electron affinity depends on the effective nuclear charge as well. Since more the effective nuclear charge, more the pulling power, right? More the pulling power means more the electron affinity. So electron affinity is directly proportional to Z effective as well. This is again one more thing which I would definitely want you guys to remember. Okay. Now similarly guys, the third thing, stability of completely filled or half filled orbitals. Stability of completely filled or half filled orbitals. For example, you have got the atom whose outermost configuration is S1 and one more atom whose outermost configuration is S2. So this is completely filled configuration. This is not completely filled, right? Perfect. If this is completely filled, it's already stable. It does not need the incoming electron. This would need the incoming electron. Perfect. So its electron affinity would be more. Let's say you have got the atom whose outermost configuration is P2 and you have got one more atom whose outermost configuration is P3. P3 is half filled, more stable, does not require the incoming electron, right? This requires. So its electron affinity would be more than that of this. So understand these sort of things, people. Understand these sort of things. Now, what kind of question is asked? The question will be pretty much simple. What is that? First of all, you should know, on moving from left to right, size decreases. And you know, electron affinity is inversely proportional to size. On moving from left to right, size decreases. If size decreases, that means electron affinity increases. On moving from left to right, electron affinity increases. On moving from top to bottom, what happens? Top to bottom, size increases. If size increases, electron affinity decreases. So down the group, electron affinity decreases. And there are some exceptions like this. When you talk about fluorine and chlorine, down the group, electron affinity decreases. So I would say fluorine should have more electron affinity than chlorine. But this is the expected order. But in reality, chlorine has got more electron affinity than that of fluorine. In reality, chlorine has more electron affinity than fluorine. Same is the case of sulfur and oxygen. Oxygen and sulfur, they belong to the same group. So down the group, electron affinity decreases. So sulfur should have less electron affinity than that of oxygen. But sulfur has more electron affinity than that of oxygen. The reason is the smaller size of fluorine, the smaller size of oxygen. The smaller size of fluorine, the smaller size of oxygen. Since fluorine, it has got the smaller size and at the same time, it has got 3 lone pairs. Right? So I would say electron density over here in case of fluorine. Electron density in case of fluorine is more. Size is less. More electrons are there. More electron density. So incoming electron will experience more repulsions. So its electron affinity will be less. Same is the case for oxygen. Size is less. Electron density is more. The repulsions towards the incoming electrons will be more. Okay? Is it clear, people? Just let me know once in the chats. And I would want you guys to remember these orders. This is basically chlorine, fluorine, bromine, iodine. One order which you have to remember. Second order of your groups, sulfur, oxygen, phosphorus, nitrogen. And this is the third order. These can be frequently asked. These are frequently asked in your examination. So remember these 3 orders. They are very, very, very important. They're very important. Okay? Now this question you can easily answer now. Tell me everyone, what is the answer of this question, quick? Everyone tell me. I think the answer is already given. No, the answer is not given. Tell me, I told you a few minutes back only. What is the answer of this question? What is the answer of this question, everyone? Fluorine, chlorine, bromine, iodine. I told you a few minutes back, chlorine has more. Chlorine has more electron gain enthalpy, or I would say electron affinity. Chlorine has more electron affinity than that of fluorine, right? So which one is the answer? Chlorine has more than of fluorine. So option C, right? Option C is the one. Absolutely. The last topic in this particular chapter, what is that? That is electronegativity. Let's see what exactly this electronegativity is all about. Then we'll move on to our next chapter, that is your chemical bonding. Okay? My dear students, what is electronegativity? Electronegativity, in simple words, the tendency of the covalently bonded atom, to attract the shared pair of electron towards itself. The tendency of a covalently bonded atom to attract the shared pair of electron towards itself. For example, there is a covalent bond between A and B. Let's say there is a covalent bond between A and B. Covalent bond is formed by the mutual sharing of electrons. So I would say this electron pair should be present at the middle. Since it's a mutual sharing, so this electron pair should be present at the middle. Now imagine B is more electronegative. If B is more electronegative, that means B has got more tendency to attract this shared pair towards itself. And when the shared pair of electron goes towards B, electron density towards B is going to increase. And that increase in electron density, I represent with delta negative. And electron density towards A is going to decrease. And that decrease in the electron density, I represent with delta positive. As simple as that. Right? Perfect, guys. So basically, there was a covalent bond between A and B. Covalent bond is formed by mutual sharing. So this electron pair was supposed to be at the center. Now B, I'm assuming to be more electronegative. And if B is more electronegative, that means B has more tendency to attract the electron pair towards itself. Right? Due to which electron density towards B will increase. Electron density towards A will decrease. Right? And if electron density towards B is increasing, that means B gets delta negative charge. A gets delta positive charge. In short. Now, electronegativity depends on certain factors. First factor on which electronegativity depends, that is size. Lesser the size, more is the electronegativity. This is the first factor. Lesser the size, more is the electronegativity. For example, fluorine, chlorine, bromine, iodine. They belong to the same group. Down the group, size increases. If size increases, electronegativity decreases. So fluorine is more electronegative than that of chlorine. Chlorine is more than of bromine. Bromine is more than of iodine. Right? Simple. Basic stuff. Guys. Electronegativity, that is inversely proportional to atomic size. Now, one more thing. Electronegativity, it depends on the effective nuclear charge as well. Now you tell me, if I say the effective nuclear charge is more, that means the pulling power is more. If the pulling power is more, it automatically means the electronegativity is more. So electronegativity depends on effective nuclear charge as well. And effective nuclear charge already directly proportional to positive, inversely proportional to negative. Now, can you arrange them on the basis of electronegativities? More the positive charge, more the effective nuclear charge, and more the electronegativity. Similarly, more the positive charge, more the effective nuclear charge, right? More the electronegativity. As simple as that. And my dear students, this electronegativity, it depends on S character as well. I believe all of you would be knowing about something about hybridization. If not, then in the next chapter, I have to discuss hybridization with you. Okay? But right here, few things I would want to tell you. If I talk about this carbon, how many sigma bonds it's forming? 1, 2, 3, 4. 4 sigma bonds means this carbon is showing sp3 hybridization. This carbon is forming 1, 2, 3. 3 sigma bonds. 3 sigma bonds means sp2 hybridization. This carbon is forming 1, 2. 2 sigma bonds, it means sp hybridization. In case of sp3 hybridization, percentage S character is going to be 25%. In case of sp2 hybridization, percentage S character is going to be how much? 1 by 3 is how much? 33%. In case of sp hybridization, percentage S character, remember directly, it's going to be 50%. It is going to be 50%. And remember, electronegativity, it depends on percentage S character. More the percentage of S character, more is going to be electronegativity. Remember this particular point, right? So here the percentage S character is 25, here the percentage S character is 33, here the percentage S character is 50%. More the S character, more the electronegativity. Okay? More the electronegativity. And you can remember this as your exception. Electronegativity of gallium is more than that of aluminium. Remember this. Electronegativity of gallium is more than that of aluminium. You can remember it directly. Now, my dear students, what are the different applications of electronegativity? Well, in terms of electronegativity, you can talk about non-metallic character. What is a non-metal? What is the tendency of a non-metal? The tendency of the non-metal is to gain electron. The tendency of the non-metal is to gain electron. Right? Metals, they lose electron. Non-metals gain electron. Perfect. And more the tendency of the non-metal to gain electron. More the tendency of the non-metal to gain electron. That means more is its non-metallic character. That means more is its reactivity. See, first of all, let me talk about two things. Reactivity of a metal depends on the tendency to lose electron. Reactivity of non-metal depends on tendency to gain electron. More the tendency of the metal to lose electron, more is its reactivity. More the tendency of the non-metal to gain electron, more is its reactivity. Remember it. Okay? So, non-metallic nature is directly proportional to electronegativity. More the electronegativity, more the tendency to attract the electron. Right? Perfect. And more tendency to attract electron means more non-metallic character. In short. Also, there is one more application of it. What is that? You can give the order of bond energy as per the electronegativity difference between the atoms. And remember, my dear students, more the electronegativity difference between the atoms, more is going to be the bond energy. So if you look at this particular equation, HF, HCl, HBr, HI, if I ask you where is the electronegativity difference more, I would say electronegativity difference between hydrogen and fluorine is more, right? And more the electronegativity difference, more is going to be the bond energy in short. Remember it as well. More the electronegativity difference between the atoms, more the bond energy. This can be the question asked. Similarly, there are few more things, my dear students, which you need to remember. What are those things? Nature of oxides. Nature of oxides. Along the period, acidic nature of oxides. Along the period, acidic nature of oxides increases, right? Down the group, basic nature of the oxides increase. Remember these two statements, they will be of very much helpful to you. Questions can be asked from it. Questions can be asked from it. Okay? Questions can be asked from it. Nature of oxides. Along the period, acidic nature of the oxides increases. Down the group, basic nature of the oxides increase. Remember this particular point. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? You can, since they are your second period elements, so along the period, acidic nature increases. Down the group, basic nature increases. Remember it. Similarly, my dear students, one more thing. Acidic strength of the oxide or oxyacid. That's also directly proportional to electronegativity. More the electronegativity, more is going to be the acidic nature of the oxide or the oxyacid. For example, here the central atom is boron, carbon, nitrogen, right? Nitrogen is more electronegative. So its oxide will be more acidic, right? Chlorine, bromine, iodine. Chlorine here is more electronegative. So its oxyacid is going to be more acidic, right? Similarly, sulfur, SET, sulfur is more electronegative. So its acid is going to be more acidic. So remember, acidic strength of oxide or oxyacid, that's also directly proportional to what? Electronegativity. And my dear students, there is one table which I would want you to remember. Anything can be asked from this particular table, and questions have been asked frequently. Okay? Look at it carefully. Basic oxides. Your metallic oxides are generally basic oxides. Non-metallic oxides are generally acidic oxides. There are some neutral oxides which you have to remember. They are asked N2O, NO, H2O, CO. They are the examples of neutral oxides. There's a direct memory based question asked. Which of the following is the neutral oxide? Which of the following is the amphoteric oxide? So you have to remember all these neutral oxides and amphoteric oxides, my dear students. They are directly asked as the memory-based question. They are directly asked as the memory-based question. Remember this. With this, we are done with the first one. That is your periodic classification. The next chapter, that is the most important one, we call it as chemical bonding. My dear students, chemical bonding will be starting after the break, and the break is till 1:20. So have your lunch. Okay? Have your lunch and get back. Have your lunch quickly and get back. And chemical bonding, I'll be completing in almost 2.5 hours. That's it. Okay? 2.5 hours. That's all. I'll see you exactly after the lunch break, and I would want every one of you to join in. Okay? See you guys. See you exactly at 1:20. Is everyone back? Is everyone back? All right. So guys, tell me, is the periodic classification chapter completely clear to everyone? Just let me know once in the chats quick. Is it like properly clear to everyone? Can you let me know quickly in the chats, every one of you? Is it like properly clear to everyone? All right. So let's get going with the new chapter. That's your chemical bonding, right? And what all topics are there in chemical bonding chapter? So first of all, we are done with this one. We are done with this one. We are done with this one, and we are done with this one. Okay, we are done with this one as well. Now, chemical bonding chapter will start from the Lewis structures. Okay. So first, we'll be covering Lewis structures, and with Lewis structures, we'll be covering formal charge as well, right? And after that, dipole moment, Fajan's rules, hybridization, VSEPR, MOT, bond angle, and hydrogen bond. These are basically the topics which are from the chapter chemical bonding, from which questions will be asked in your NEET exam. Okay, so let's get going. Let's get started with your chemical bonding chapter. Let's get going with your chemical bonding chapter. And my dear students, the first topic which I'll be discussing in the chemical bonding chapter, what is that? That is, how do we draw the Lewis structures of different simple molecules? How do we draw the Lewis structures? How do we draw the Lewis structures of different molecules? This is important, and my dear students, I would want you guys to understand and remember how do we draw the structures. Understand properly now. For example, I have got the molecule CO, carbon monoxide. Okay, carbon monoxide. I have to draw its Lewis structure. How do I exactly draw it? My dear students, first of all, can you tell me how many valence electrons carbon has? If I talk about carbon, carbon has got 4 valence electrons. If I talk about oxygen, how many valence electrons oxygen has? 6 valence electrons. So in this molecule, how many total valence electrons do we have? 10 valence electrons in total. In this molecule, we have got 10 valence electrons. My dear students, 10 valence electrons means 5 valence electron pairs, because one pair contains 2 electrons. One pair contains 2 electrons. So 5 pairs will contain 10 electrons. So I would say 10 valence electrons means 5 valence electron pairs. Okay. Now, we have to draw the structure of carbon monoxide. This is carbon, this is oxygen. Carbon and oxygen. The first thing, my dear students, put a single bond between carbon and oxygen. Put a single bond between carbon and oxygen. Single bond means 1 electron pair. Single bond means 1 electron pair. So I had 5 valence electron pairs, out of which 1 electron pair I have used. 1 electron pair I have used. Now, which one is more electronegative among carbon and oxygen? I would say oxygen is more electronegative. So start filling the octet of oxygen. Start filling the octet of oxygen. How exactly? See, 1, 2, 3, 4, 5, 6, and 7, 8. So octet of oxygen is completed. How many valence electron pairs I had? 5. Out of 5, how many I have used? 1, 2, 3, and 4. 4 electron pairs I have used. 1 is left. Give that 1 electron pair to carbon. Now check the octet of both atoms. Octet of oxygen is complete. 2, 4, 6, and 8. It's complete. What about the octet of carbon? 2 and 4. Octet of carbon is not complete yet. So we have to complete the octet of carbon as well. For that, what I'll be doing? I'll be removing one electron pair from oxygen and put a single bond. I'll be removing one more electron pair from oxygen and put a single bond. Now check the octet of both the atoms. 1, 2, 3, 4, 5, 6, 7, 8. Completed. What about carbon? 1, 2, 3, 4, 5, 6, 7, 8. Octet of both atoms is complete. So this is the Lewis structure of your carbon monoxide. Now, my dear students, now there is one more point. How do we calculate formal charge? Let's say I need to calculate formal charge on carbon. How do I calculate formal charge on carbon? First of all, tell me when carbon is in non-bonded state. When carbon is in non-bonded state, how many valence electrons it has? Carbon, when present in non-bonded state, it has got 4 valence electrons. It has got 4 valence electrons in non-bonded state. Minus. How many electrons carbon has right now? 1, 2. Out of this, 1 belongs to carbon. Out of this, 1 belongs to this. Out of this, 1 belongs to this. 1, 2, 3, 4, 5. So 4 minus 5 is equal to minus 1. So minus 1 is basically the formal charge on this carbon over. Similarly, if I ask you, what is the formal charge on oxygen? What is the formal charge on oxygen? Tell me. When oxygen is in non-bonded state, oxygen when present in non-bonded state, how many valence electrons oxygen has? 6 minus. Right now, how many it has? 1, 2, 3, 4, 5. So 6 minus 5 is equal to plus 1. So formal charge on carbon is minus 1. Formal charge on oxygen is plus 1. As simple as that. This is how you draw the Lewis structures, and this is how you get the formal charges on different atoms. Let me take a few more examples. With that, things will be more clear to you. My dear students, for example, I need to draw the structure of CO3 dinegative. I need to draw the structure of CO3 dinegative. How do I draw the Lewis structure of CO3 dinegative? First of all, how many valence electrons carbon has? 4. How many valence electrons oxygen has? 6. And there are 3 oxygen atoms. Since there is a negative charge, so if there is a negative charge, add that. So this was dinegative, so I've added it, plus 2. So 6, 3, 18. 18 plus 2 is 20. 20 plus 4 is 24. So in total, there are 24 valence electrons. So that means how many valence electron pairs do we have? We have got 12 valence electron pairs. We have got 12 valence electron pairs. Now, which one is less electronegative? Carbon. Remember, less electronegative element will be your central atom. Less electronegative element will be your central atom. And there are 3 oxygen atoms. So I'll put these 3 oxygen atoms over here. Now do one thing. Put a single bond everywhere. So that means 3 electron pairs I've used. 3 electron pairs I've used. Now start filling the octet of more electronegative elements. Start filling the octet of oxygen atoms. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? The octet of all the 3 oxygen atoms is complete. Now check the octet of carbon. Is the octet of carbon complete? 2, 4, 6. Octet of carbon is not complete. Now do one thing. Select any oxygen. Select any oxygen. Remove one of the electron pair. And instead of that, put a double bond. Now check. Is the octet of carbon complete? 2, 4, 6, 8. Complete. Is the octet of this oxygen complete? 2, 4, 6, 8. It's complete. Right? So this is going to be the structure of your CO3 dinegative. Now, let's call this as oxygen 1. Let's call this as oxygen 2. Let's call this oxygen 3. Now, let's calculate the formal charge on oxygen number 1. Let's calculate the formal charge on oxygen number 1. Oxygen in non-bonded state has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, 5, 6, and this. 7. So 6 minus 7 is equal to minus 1. What is the formal charge on oxygen number 2? Oxygen in non-bonded state has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, 5, and 6. So 6 minus 6 is 0. Its formal charge is 0. What about oxygen number 3? Formal charge on oxygen number 3. In non-bonded state, 6. Right now, 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is equal to minus 1. What about the formal charge on carbon? What about the formal charge on carbon? Carbon in non-bonded state has got 4 valence electrons. Minus. Right now, how many it has? 1, 2, 3, and 4. Right? 4 minus 4 is 0. So formal charge on carbon here is 0. I believe you got to know how do we draw the structures of different compounds and how do we calculate the formal charges. Am I clear to everyone? Am I clear to everyone, people? Quickly, let me know in the chats. Let me take one more example. With that, things will be more clear to you. Let me take one more example. With that, things will be more clear to you. Yeah? So first of all, Cn negative. How many valence electrons carbon has? 4. Nitrogen, 5. There is a negative charge, so add that. So 5 plus 1 is 6, 6 plus 4 is 10. So 10 valence electrons. 10 valence electrons means how many pairs? 5 valence electron pairs. Now this is carbon, this is nitrogen. Put a single bond. Now start filling the octet of more electronegative element. 1, 2, 3, 4, 5, 6, 7, 8. Done? Okay. Now out of 5 valence electron pairs, how many I have used? 1, 2, 3, and 4. 4 electron pairs I have used. So put 1 here on carbon. Now check the octet of carbon. 1, 2, 3, 4. It's not complete. So remove this electron pair and put a single bond here. Remove one more electron pair on nitrogen. Put a single bond here. Now check the octet of both the atoms. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Octet of both of them is complete. Now, if I need to calculate the formal charge on this particular carbon, it is going to be carbon in non-bonded state has got 4 valence electrons minus. Right now, how many it has? 1, 2, 3, 4, 5. So 4 minus 5 is minus 1. Similarly, formal charge on nitrogen. Nitrogen in non-bonded state has got 5 valence electrons minus. Right now, how many it has? 1, 2, 3, 4, 5. So 5 minus 5 is 0. So these are the formal charge on carbon and nitrogen here. Am I clear with this? I believe these sort of things you can easily check from now onwards, right? These sort of things you can easily check from now onwards. And this is going to be your homework question. You can check this out. You can draw its Lewis structure and you can get the formal charges on both the oxygen atoms. Okay? Sir, you did not send the biology 340 plus PDF. Did I not send that? I'll check that out. I will check that out. Don't worry. Tell me in the chats, is every single thing clear, people? Is every single thing clear till here? Let me know once in the chats quick. Now, my dear students, the second topic, the next topic I mean, which I'm going to discuss here in chemical bonding, what is that? That is going to be your dipole moment. That's going to be your dipole moment. This is again a topic from which question will be directly asked in your NEET examination. And I'll tell you only those things which are required basically to solve the questions based on dipole moment, right? No irrelevant stuff I'm going to tell you right now. Okay? Now, what is a dipole moment? First of all, people, whenever you will have equal and opposite charges, whenever you will have equal and opposite charges separated by some distance, whenever you have got equal and opposite charges separated by some distance, let me tell you, the system of equal and opposite charges, the system containing equal and opposite charges separated by certain distance, the system of charges is what you call as dipole. Dipole is nothing but it is the system containing equal and opposite charges separated by certain distance. System of equal and opposite charges separated by certain distance. The system of charges which is separated by some distance is what you call as dipole. And my dear students, for the dipole, what do we define? For the dipole, we define its moment. For the dipole, we define its moment. Dipole moment, which is represented by mu. And how do we define this dipole moment? It is nothing. It is the product of charge, product of magnitude of charge, and the distance between the charge. And let me tell you this dipole moment, as you all must be familiar with the fact, it's a vector quantity. It is a vector quantity. The SI unit of dipole moment is what? SI unit of dipole moment is d by. SI unit of dipole moment is d by. Since dipole moment is a vector quantity, so it will be having some direction as well. And in chemistry, the direction of dipole moment is taken from less electronegative element to more electronegative element. Or I can say its direction is taken from positive to negative. Its direction is taken from positive to negative. The direction of moment in chemistry is taken from positive to negative, or you can say from less electronegative element to more electronegative element. Okay? Now, my dear students, few more things. For example, you have got a molecule HCl. If I ask you among hydrogen and chlorine, which one is more electronegative? Your answer will be chlorine. Chlorine is more electronegative. If chlorine is more electronegative, it has got more tendency to attract the electron pair towards itself. If chlorine is more electronegative, definitely it will be how? It will be having more tendency to attract the electron pair towards itself, due to which chlorine gets delta negative charge and hydrogen gets delta positive charge. Chlorine gets delta negative, hydrogen got delta positive. Now tell me one thing. Do you see equal and opposite charges separated by certain distance? Yes. So I will be calling this as dipole. And for the dipole, what do we define? We define dipole moment. And the direction of dipole moment is from less electronegative element to more electronegative. Less to more. Yeah? Less to more. Perfect. All right. And my dear students, one more thing. Any molecule whose net dipole moment is non-zero, any molecule whose net dipole moment is non-zero, we call that particular molecule as the polar molecule. We call that particular molecule as a polar molecule. And any molecule whose net dipole moment is zero, we call that molecule as the non-polar molecule. Non-polar molecule. Now, how do we check whether the net dipole moment of the molecule is zero or non-zero? For example, I am taking the molecule BeCl2. Let's say this is the molecule BeCl2. Now tell me one thing. Beryllium and chlorine, which one is more electronegative? Chlorine, right? So this will get delta negative, this will get delta positive. Similarly, this gets delta negative, this gets delta positive, right? So this bond will be having some moment from positive to negative or less to more, less electronegative to more electronegative element. So two equal and opposite moments will get cancelled out. So I would say net dipole moment of this molecule is zero. If net dipole moment of this molecule is zero, so definitely it's going to be a non-polar molecule. Now, people, there is one thing which I would want you guys to remember for now. Okay? There is one thing which I would want you guys to remember for now. What is that thing? Whenever you see the molecule of the type Ab2L0, how do we check the type of the molecule? I'll show that in some time. How do we check the type of the molecule? I'll show that in some time. First of all, you remember, whenever you see a molecule of the type Ab2L0 or Ab3L0 or Ab4L0 or Ab5L0 or Ab6L0 or Ab7L0 or Ab2L3 or Ab4L2, Ab4L2. Whenever you see molecules of this type, any of these types, remember, these molecules will have net dipole moment 0 and they are going to be called as the non-polar molecule. They are going to be called as the non-polar molecule. Remember this particular statement, question will be asked from this. And we will at the same time, there is one more thing that I would want to share with you. What is that? Remember, lone pair also contributes. Lone pair also contributes towards the moment. Lone pair also contributes towards the moment. Towards the moment. And the direction is from, and the direction is towards the lone pair. And the direction is towards the lone pair. What does it mean? Have a look. For example, I am taking the molecule NH3. I am taking the molecule NH3. Now, all of you must be knowing nitrogen has got one lone pair. Nitrogen has got one lone pair. As I told you, lone pair also contributes towards the moment. And the direction due to the lone pair is towards the lone pair, like this. Direction due to lone pair is towards the lone pair, right? Direction due to this particular bond is from less electronegative to more electronegative. Less electronegative to more electronegative. Less electronegative to more electronegative. And this lone pair also contributes towards the moment. Its direction is towards the lone pair. Remember it as well, because this is something on which question will be framed. Perfect. Just give me a second, guys. Just give me a second. Done? Okay. Now let's see what kind of questions can be framed here. My dear students, one more thing which I would want you guys to remember here. What is that? Just one thing. Remember when you have to give the order of the dipole moment. Whenever you'll have to give the order of the dipole moment. Okay. How do you give the order of the dipole moment? The first thing always, remember, more the electronegativity difference between the atoms, more the electronegativity difference between the atoms, more is going to be the dipole moment. Remember this particular point. More the electronegativity difference between the atoms, more is going to be the dipole moment. Okay, this is the first factor which you should remember. Now try to understand what I'm going to say. You have got, first of all, for example, this particular question. HF, HCl, HBr, HI. Can you tell me where is the electronegativity difference more? I would say in HF, since fluorine is more electronegative, then chlorine, then bromine, then iodine. So electronegativity difference here is more. And more the electronegativity difference, more is going to be the dipole moment. Simple. Okay, number one. Number two. CCl bond here, CCl bond here. Right? So the moment direction is from less electronegative to more, less electronegative to more. So I would say net dipole moment will be in this direction. Okay. Now, less to more will get cancelled out. So where is the net dipole moment more? In the first case. In the first case. Now, NH3 and NF3. NH3 and NF3. Remember, NH3 has got more dipole moment than that of NF3. Okay. NH3 has got more dipole moment than that of NF3. Similarly, guys, for example, this is one more question. You have to arrange them on the basis of their dipole moments. I believe all of you would have studied GOC once, and you would be knowing CH3. It's electron donating group. It is electron donating group, right? CH3, electron donating group. If it is electron donating, it donates electrons. When it donates electron, it gets delta positive, this gets delta negative. Similarly, delta positive, delta negative. So moment from positive to negative will cancel each other and net is zero. Net is zero, right? Look at this. Since it is donating means positive, negative to negative. Similarly, positive to negative. Similarly, positive to negative. Similarly, positive to negative. Right? Now, if you look at these two cases, one moment is going downwards, one moment is going in this direction. So the angle between them is 120. Similarly, one moment is pointing downwards, one moment is going in this direction. So the angle here is 60. And lesser the angle between two vectors, more is the resultant. So where will be the resultant more? In third, followed by 2, followed by 1. This is the order of the dipole moment. Right? This is the order of the dipole moment. Look at the next one. CH3, it is donating group. This NO2 is withdrawing group. CH3 is electron donating. NO2 is electron withdrawing. If CH3 is electron donating, it will get delta positive, delta negative. This is electron withdrawing. This gets delta negative, this gets delta positive. Let me give all the charges first. Delta positive, delta negative. Delta negative, delta positive. Delta positive, delta negative. Delta negative, delta positive. Now, give the direction. Positive to negative. Positive to negative. That means one vector is pointing downwards. One vector is going in this direction. Right? At an angle of 120. Positive to negative. Positive to negative. One vector going downwards. One vector is going in this direction. Angle here is 60. Positive to negative. Positive to negative. Both the vectors are going in the same direction. Angle here is 0. And you know, lesser the angle between the two vectors, more is the resultant. So I would say 3 will have more dipole moment, followed by 2, followed by 1. Let me know once in the chats if this is clear. Let me know once in the chats if this is clear. Okay, guys. These are some special cases. Okay, these are some special cases here. Can you tell me among these three molecules, where is the net dipole moment 0 and where is it non-zero? Can you tell me quick? Can you tell me where is the net dipole moment 0, where is it non-zero? See, in the first case, Cl, more electronegative, right? Delta negative, delta positive. So from positive negative, so from positive negative. Cancels out, net dipole moment is 0 here. And these are the two cases wherein it looks like net dipole moment is 0. But remember, their net dipole moment is non-zero. Their net dipole moment is, okay? Remember these two cases directly. Remember these two cases directly. Okay, there is one more thing as well. There is one more thing as well. What is that? For example, you have got the molecule CH3F. You have got the molecule CH3Cl. You have got the molecule CH3Br. You have got the molecule CH3I. Okay. Now, as I told you, dipole moment is nothing but it is charge multiplied by distance. It is charge multiplied by distance. Right? More the charge, more the dipole moment. And more charge will be due to more electronegativity difference. More charge will be due to more electronegativity difference. Now, try to understand what I'm going to say. First of all, here you have got a bond between carbon and fluorine. Here the bond is between, here the bond is between carbon and fluorine. Here the bond is between C and Cl. Here the bond is between C and Br. And here the bond is between C and I. Now, as per the charge factor, more the electronegativity difference, more is the dipole moment. More the electronegativity difference, more is the dipole moment. Where is the electronegativity difference more? In CF, I would say, as per charge factor, CF, as per charge factor, I would say, one should have more dipole moment than that of 2. But there is one more factor also, that is distance factor. Now, do you see CCl bond length? CCl bond length is more than that of CF bond length. If CCl bond length is more, I would say 2 should have more dipole moment than that of first because of distance factor. And out of the two factors here in this case, distance factor dominates. So net dipole moment order is 2 greater than 1 greater than 3. This is the actual order. Remember this particular case properly. This is the question wherein distance factor dominates over the charge factor. If I'm clear, let me know once in the chats. Quick. Perfect. Okay. Can you tell me the answer of this question? For example, I have got the question like this. H2O, H2S. Can you tell me which one has got more dipole moment? Here the bond is between OH. Here the bond is between SH. Electronegativity difference between O and H is more. More the electronegativity difference, more is the dipole moment. In short, this is the only question wherein distance factor dominates. In all the other questions, you have to see what? You have to see the electronegativity difference. That's it. That's it, people. Right? For example, you have got NH3, PH3. You have got NH3, you have got PH3. Can you tell me where is the dipole moment more? NH3 or PH3? Quick. Quickly, guys. NH3 or PH3? Here the bond is between N and H. Here the bond is between P and H. Where is the electron negativity difference more? In case of N and H. Electron negativity difference is more. And more the difference, more the dipole. So these sort of questions are framed in your examination. And my dear students, you should be in a position to solve each one of them from now on. Okay? My dear students, now there comes a term called as Fajan's rules. Right? There comes a term called as Fajan's rule. Where do we use the concept of Fajan's rules? That's the first point. When do we use Fajan's rules? First of all, whenever you are given with some molecules, 3-4 molecules, and you have to check which one has got more covalent character, which one has got more ionic character, right? You would have find a lot of questions like that, wherein they'll ask you which one of the following has got more covalent character, which one of the following has got more ionic character, right? In those questions, you use the concept of Fajan's rule. Use the concept of Fajan's rule. And few things I would want you guys to remember, and you are sorted. You are done. You are done. What is that? Let me tell you. Covalent character in an ionic bond. Covalent character in an ionic bond. Is it directly proportional to the polarizing power of cation? Also directly proportional to the polarizability of anion. What is polarizing power? What is polarizability? We have got nothing to do with that right now. Just remember one thing. Whenever you have to give the order of the covalent character of different molecules, remember covalent character, it depends on two factors. One is polarizing power of cation. One is polarizability of anion. And this polarizing power of cation, it depends on two factors. Directly proportional to charge on cation, inversely proportional to size of cation. Polarizability of anion, it also depends on two factors. Charge on anion as well as size of anion, and directly proportional both. Okay? And remember, covalent character is inversely proportional to ionic character. These are few things which you need to remember, and you can solve the questions based on Fajan's rules easily. Now, let me quickly summarize it. Whenever you are given with 3-4 molecules and you have to arrange them on the basis of covalent character, covalent character in an ionic compound depends on two factors. One is polarizing power of cation, one is polarizability of anion, right? And covalent character is directly proportional to polarizing power of cation, also directly proportional to polarizability of anion, right? And my dear students, at the same time, let me tell you, polarizing power of cation is directly proportional to charge on cation, inversely proportional to size of cation. Polarizability is directly proportional to charge on anion, directly proportional to size of anion. And remember, covalent character is inversely proportional to ionic character. That's all. Now let's have a look what kind of questions can be framed. For example, I have to arrange them on the basis of the polarizing power. I have to arrange these cations on the basis of polarizing power. Now, how you are going to arrange them? More the positive charge, more the charge on the cation, more the polarizing power. More the charge on the cation, more the polarizing power. Few minutes back only I told you. More the polarizing power, more the charge. More the charge on the cation, more the polarizing power. Polarizing power also depends on size. And polarizing power of cation is inversely proportional to size. It is inversely proportional to size. Look here carefully. Charge on every cation is same. Charge on every cation is same. Lithium, sodium, potassium, rubidium, cesium. Charge everywhere is same. +1, +1, +1. Now, when you go down the group, lithium, sodium, potassium, rubidium, cesium, down the group size increases. Polarizing power and size, they are inversely proportional. So, lesser the size, more the polarizing power of cation. Lesser the size, more the polarizing power of cation. Lesser the size, more the polarizing power of cation. Right? Right, people? If I talk about the D block elements, my dear students, in case of D block elements, let's say you've got Fe dipositive, CO dipositive, nickel dipositive, copper dipositive. On moving from left to right, effective nuclear charge increase, due to which polarizing power of cation also increase. So remember, polarizing power of Cu dipositive will be more than that of Ni dipositive, cobalt dipositive, iron dipositive. So in case of D block elements, polarizing power is directly proportional to what? Effective nuclear charge. Is directly proportional to effective nuclear charge. As simple as that. Now similarly, there is one more thing. When you move from 3D series to 4D, 4D to 5D, then you move from 3D to 4D, 4D to 5D. Remember, polarizing power again increases. When you move from 3D to 4D, 4D to 5D, polarizing power again increase. And there are few things which you can remember here. For example, zinc dye positive, cadmium dye positive, mercury dye positive. This is 3D. Just a second, guys. There is an electricity cut. We will have to use less light for some time. Okay. This zinc dye positive, it is the 3D element. This is the 4D element. This is the 5D element. I told you a few minutes back, from 3D to 4D, 4D to 5D, polarizing power increases. Hg dye positive, more polarizing power. CD dye positive, then zinc dye positive. Okay. Similarly, if I talk about the polarizability of anion. Polarizability of anion depends on two factors: charge on anion, size of anion. And polarizability of anion is directly proportional to charge on anion, also directly proportional to size of anion. Something which I told you a few minutes back only. Now, if you look carefully, N tri-negative, O di-negative, F negative. We have to arrange these anions on the basis of polarizability. More the charge on anion, more the polarizability. More the charge on anion, more the polarizability. Okay? Now, more the charge on anion, more the polarizability of anion. Right? Now, similarly, you can talk in terms of size. You can talk in terms of size as well. You've got F negative, Cl negative, Br negative, I negative. In all these anions, the charge is same. Now we have to talk in terms of size. Fluorine, chlorine, bromine, iodine. Down the group, size increases. More the size of anion, more the polarizability. Right? Oxygen, sulfur belong to same group. Oxygen, sulfur. Down the group, size increases. More the size, more the polarizability of anion. More the size, more the polarizability of anion. As simple as that. Right? Remember these things, guys. Now you can easily solve the questions which are based on Fajan's rules. For example, these are the questions. You have to give the order of covalent character. How do you give the order of covalent character? Understand. First of all, this will be zinc dye positive. This will be Cl negative. Cadmium dye positive, Cl negative. Hg dye positive, Cl negative. Right? Now, my dear students, anion everywhere is same. So I'm not going to decide on the basis of anion. I'll be deciding on the basis of cation. The charge on every cation is same. But if you think carefully, this is 3D element, this is 4D, this is 5D. 5D element has got more polarizing power. More the polarizing power of cation, more the polarizing power, more will be the covalent character. More the polarizing power, more will be the covalent character. As simple as that. Similarly, again, this is zinc dye positive, cadmium dye positive, mercury dye positive. This cation will be having more polarizing power, so more covalent character. More polarizing power means more covalent character. Perfect. Similarly, if you look carefully, this is Li positive, F negative, Na positive, F negative, K positive, F negative, Rb positive, F negative, Cs positive, F negative. See, anion everywhere is same. Now decide on the basis of cation. Anion everywhere is same. So decide on the basis of cation. Now, Li positive, Na positive, K positive, Rb positive, Cs positive. Now, I would say this cation has got lesser size. Lesser the size of cation, more the polarizing power of cation. More polarizing power of cation means more covalent character. More covalent character. This is Be dye positive. Be dye positive. Leave that. Now this is F negative, Cl negative, Br negative, I negative. So decide on the basis of anion here. The charge on every anion is same. So you'll be talking in terms of size. More the size of anion. More the size of anion. More will be the polarizability of anion. And more polarizability of anion means more covalent character. Okay? Am I clear? People? Am I clear? This is one more important parameter which you need to remember. My dear students, polarizing power of the cation that shows pseudo inert gas configuration is always more than that of polarizing power of that cation which has got inert gas configuration. Now, what is pseudo inert gas configuration? What is inert gas configuration? Whenever you see electronic configuration of an element like this, inert gas followed by D10. For example, you have got Cu positive. Right? If you talk about the electronic configuration of Cu positive, it will be argon followed by D10 configuration. So noble gas followed by D10 configuration. You call it as pseudo inert gas configuration. You've got Na positive. Na positive, its configuration is simply the configuration of neon. So Na positive has got inert gas configuration. This is what you call a pseudo inert gas. This is what you call as inert gas. And that cation which shows pseudo inert gas configuration, its polarizing power is always more than the cation which has got inert gas configuration. So on this, you can just solve one question. Tell me the answer of this question. Give the order of covalent character here. Give the order of covalent character here, quick. Give the order of covalent character here, quick. Everyone. Quickly, guys, everyone. Absolutely, your CuCl will have more covalent character than that of NaCl. Why is that? Because Cu positive has got pseudo inert gas configuration, and that cation which has got pseudo inert gas configuration, that is having more polarizing power. More the polarizing power of cation, what is going to be the covalent character? As simple as that, right? So these are the questions, my dear students, which can be framed from your Pajan's rules. Now comes one more topic. What is that? That is, how do we calculate hybridization? What is hybridization, etc., etc.? We have got nothing to do with that. The point is simple. You get questions wherein they'll ask you, how do we calculate the hybridization? How do we check the hybridization? So let me tell you, how do we exactly check the hybridization? My dear students, there's a rule. There's a rule by means of which we can calculate hybridization of an element. How do we check the hybridization? There's a rule. The rule is called as the steric number method. It is called as the steric number method. In steric number method, what do we need to calculate? We need to calculate steric number of that atom. We need to calculate steric number of that atom whose hybridization we have to check. In steric number method, we have to calculate the steric number of that atom whose hybridization we have to calculate. And steric number is nothing but it is the sum of sigma bonds formed by the central atom plus the lone pairs which are there on the central atom. Steric number is nothing. Sigma bonds formed with the central atom plus the lone pairs which are there on the central atom. How do we check the sigma bonds? How do we check the lone pairs? You'll understand in some time. But before that, you need to remember a few things. What are those things? My dear students, if the steric number comes out to be 2, if the steric number comes out to be 2, remember the hybridization involved is going to be sp. And the geometry predicted through hybridization is what you call as the linear geometry. If the steric number is 3, hybridization involved is sp2, the geometry predicted is trigonal planar. Right? If the steric number is equal to 4, hybridization will be sp3 and the geometry predicted through hybridization is going to be tetrahedral. Tetrahedral. And similarly, if the steric number is equal to 5, The hybridization involved is going to be sp3d, and the geometry is going to be trigonal bipyramidal. Trigonal bipyramidal. Similarly, if the steric number is equal to 6, hybridization involved is going to be sp3d2. The geometry predicted through hybridization is going to be octahedral. And similarly, if the steric number comes out to be 7, the geometry predicted through hybridization is sp3d3. And I would say the hybridization is going to be sp3d3, and the geometry predicted through hybridization is going to be pentagonal bipyramidal. Okay. These are few things which you need to remember first of all. Now, guys, if you look at all these cases wherein the hybridization is sp3d, sp3d2, sp3d3, they can ask you which d orbital is involved in hybridization here. Remember, it is going to be dz square, which is involved here in the hybridization. Which d orbital is involved here? Remember, it's going to be dx square minus y square and dz square, which are involved in hybridization here. In d3 hybridization, it's going to be dx square minus y square, it's going to be dz square, it's going to be dx. These are the d orbitals which are involved in the hybridization in case of sp3d3. Okay. So these are first of all few things, my dear students, which you have to remember. When the steric number comes out to be 2, sp. Steric number 3, sp2, 4, sp3, 5, sp3d, 6, sp3d2, 7, sp3d3. And these are the geometries which are predicted through hybridization. Now the point is, how do we exactly check the hybridizations of different molecules? How do we exactly check the hybridizations of different molecules? Okay, let's have a look. Let's have a look, people. Understand what I'm going to say. Understand what I'm going to say. For example, I have to calculate the hybridization of this carbon here. Okay. Tell me how many valence electrons carbon has. Carbon has got 4 valence electrons. Carbon has got 4 valence electrons. How many surrounding atoms do you see here? 4 surrounding atoms. Remember, the number of surrounding atoms is equal to the number of sigma bonds. The number of surrounding atoms is equal to the number of sigma bonds. Now, out of 4 valence electrons which carbon had, I would say carbon had 4 valence electrons. It is forming 4 sigma bonds. That means carbon has utilized all the 4 valence electrons to form 4 sigma bonds. Carbon has utilized all the 4 valence electrons to form 4 sigma bonds. So will there be any lone pair on carbon? No. Steric number will be sigma plus lone pair. 4 plus 0, that's 4. So hybridization involved is sp3. Simple. Right? Similarly, BF3. Talk about boron. How many valence electrons boron has? 3 valence electrons. Right? How many surrounding atoms do you see? 3. So number of surrounding atoms is equal to number of sigma bonds. So boron had 3 valence electrons, and all the 3 valence electrons are utilized, form 3 sigma bonds. How many lone pairs on boron? 0. Steric number, sigma plus lone pair, 3. Hybridization. Isn't it simple? Right? Similarly, guys, for example, BeCl2. How many valence electrons beryllium has? It has 2 valence electrons. How many surrounding atoms? 2. So sigma bonds 2. 2 valence electrons. Beryllium had 2 valence electrons. It formed 2 sigma bonds. All the 2 valence electrons are utilized. Form 2 sigma. There is no lone pair on it. Steric number. Sigma plus lone pair. Right? Hybridization. sp. Right? Similarly, guys, look at this one. PCl5. PCl5. Phosphorus. How many valence electrons? 5. How many surrounding atoms? 5. So how many lone pairs on phosphorus? 0. Steric number. Sigma plus lone pair. 5. Hybridization. P3D. Simple. SF6. Valence electrons. 6. Right? Surrounding atoms. 6. Lone pairs on sulfur. 0. Steric number. 6. Hybridization. sp3d2. Perfect. Am I clear, people, till here? Am I clear till here, every one of you in the chats? Let me take few more cases. Let me take few more cases. For example, you have got NH3. For example, you have got NH4 positive. For example, you have got XCF2. For example, you have got I3 negative. I3 negative. Let's say we have got NO2 negative. Okay. Let's say we have got what? What else? For example, you have got XCOF4. For example, you have got XeO2F2. Now let's check the hybridization one by one. For example, this nitrogen. Valence electrons nitrogen has 5. Surrounding atoms are 3. Therefore, 3 sigma bonds. Out of 5 valence electrons, 3 are used to form 3 sigma bonds. So 2 will be left as such on nitrogen in the form of a lone pair. Steric number is 3 plus 1, 4. If steric number is 4, hybridization will be sp3. Simple. Right? You have got NH4 positive. How many valence electrons nitrogen has generally? 5. There's a positive charge, so subtract that. So 5 minus 1 makes it 4. How many surrounding atoms? 4. Therefore, sigma bonds are 4. So out of 4 valence electrons, all these 4 valence electrons are being utilized to form 4 sigma bonds. So there is no lone pair on nitrogen. Steric number 4 plus 0 is 4. Hybridization. XCF2. Valence electrons with xenon 8. Surrounding atoms 2. Sigma bonds are 2. So out of 8 valence electrons of xenon, 2 are utilized. So 6 are left as such in the form of how many lone pairs? 3 lone pairs. So steric number, sigma plus lone pair, 3 plus 2, 5, right? Hybridization, P3D, sp3D. Okay? Perfect. Now similarly, I3 negative. First of all, this I3 negative, I can write it as I2 negative. Just to make it simple, I2 negative. Let this be my central atom. So how many valence electrons with iodine? 7. Since there is a negative charge, so add it. 7 plus 1 makes it 8. Surrounding atoms are 2. Therefore, 2 sigma bonds. Out of 8 valence electrons, 2 are utilized to form 2 sigma bonds. So 6 are left as such on iodine in the form of 3 lone pairs. So lone pairs 3. Steric number 3 plus 2, 5. Hybridization P3D, sp3D. Now, I need to calculate the hybridization of this nitrogen. How do I do it? How many valence electrons nitrogen has? 5. There is a negative charge. Add it. So 5 plus 1 makes it 6. How many surrounding atoms? Surrounding atoms are 2. So 2 sigma bonds. Now, when oxygen is the surrounding atom, you have to do something different. When oxygen is the surrounding atom, you have to do something different. You will consider as if one oxygen is forming a double bond. You will consider, for example, there is oxygen attached. You will imagine as if these oxygens are attached with nitrogen with the form of double bond, with the help of double bond. Let's consider that. See, how many valence electrons nitrogen has? 6. How many sigma bonds? 2. Right? But imagine as if these 2 oxygens are forming 2 double bonds with nitrogen. Imagine these 2 oxygens are forming 2 double bonds with nitrogen. So out of 6 valence electrons, how many will be utilized? Out of 6 valence electrons, I'll say 4 would have got utilized. Because nitrogen, double bond O. 4 will be utilized. So 2 will be left as such on nitrogen in the form of lone pair. So lone pair is going to be 1. Steric number, sigma plus lone pair, 3. Hybridization. XeOF4. Xenon. How many valence electrons? 8. How many surrounding atoms? 4 plus 1, 5. Let's talk about lone pairs. 8 valence electrons. Out of 8, how many are used? 4. And oxygen is double. So imagine this is Xc. These are 1, 2, 3, 4. 4 fluorine. And this is double bonded oxygen. Right? A rough structure I'm making here. So out of 8, how many are used? 1, 2, 3, 4, 5, 6. 2 will be left as such on xenon in the form of a lone pair. Steric number is 5 plus 1, 6. Hybridization will be sp3d2. sp3d2. Perfect. Now, the answer of this question, you'll let me know in the comment section of this video. Is it clear? Everyone in the chats? Is it clear, people? Is it clear? Is it clear? Everyone means everyone. Yes? Perfectly done. Let me teach you one more thing here only. What is that? This carbon is the central atom. Let the central atoms represent by A. Let the central atoms represent by A. How many sigma bonds do you saw? 4. So I'll write B4. How many lone pairs did you see? 0. L0. The type of the molecule is AB4L0. BF3. Let boron is the central atom. How many bond pairs it's forming? 3. So B3. How many lone pairs? 0. Let the central atom is A. How many bond pairs do you see? 2. Lone pairs? 0. Similarly, the type of this molecule, now quick, AB5L0. Type of this molecule, AB6L0. Right? Similarly. Tell me, the type of this molecule, it's going to be AB3L1. AB3L1. The type of this molecule will be AB4L0. Type of this molecule will be AB2L3. Type of this molecule is going to be AB2L3. AB2L3. Type of this molecule is going to be AB2L1. Type of this molecule is going to be AB5L1. Type of this molecule. You can check that on your own. So this is how you check the type of the molecules as well. Okay? This is how you check the type of the molecules as well. Am I clear, people? So this is how you check the hybridization and the geometry which is predicted through hybridization. Okay? Geometry which is predicted through hybridization. Perfectly done? Yeah? Is it clear, guys? Everyone in the chats once? Is it clear once, everyone in the chats? Did you understand how do we get the type of the molecule as well as the hybridization? I'm asking everyone. Now there are 3 to 4 topics which are left. But before doing those topics, let's take a small break here. Let's take a small break of 15 minutes. Small break of 15. Small break of 15 minutes. You have your tea. I'll also have my tea and come back. It's 2:24 right now. 2:35, 2:40. But I would want every one of you to be back because we just have got some almost 4 topics left and we are done. We are sorted. Okay? Just 15-minute break and I'll be back. Sir, if you know how to solve, then why don't you become the doctor? Because I was the PCM student. I was not the PCB student. Okay? I'm an engineer by profession. All right? I'll see you exactly at 2:40. Be back on time because we have got just 4 topics, 4 important topics left. And it will not take more than 1.5 hours. Okay? See you. Is everyone back? Is everyone back? Yes. All right. So, my dear students, our new topic is going to be the VSEPR, valence shell electron pair repulsion theory. Okay. Valence shell electron pair repulsion theory. First of all, from this valence shell electron pair repulsion theory, what kind of questions are asked? What kind of questions can be framed from this? What kind of questions can be framed from this? Let me talk about that first. My dear students, a lot of questions you'll get wherein they'll ask you, what is the shape of the molecule? What is the shape of the molecule? Right? And questions frequently have been asked about the shapes of the molecule. And how do we check the shapes of the molecules? There are few things which you need to remember for that. First of all, with the help of the valence shell electron pair repulsion theory, we'll get to know about the actual shape of the molecule, right? We'll get to know about the actual shape of the molecule, number one. Number two, my dear students, for example, if you talk about NH3 molecule, this is your NH3 molecule, correct? Now, nitrogen has got 5 valence electrons, out of which 3 electrons have been used for bonding. 3 electrons are used for bonding. And those electrons which are used for bonding, you call them as the bonding electrons. These 2 electrons, which belong to the valence shell of nitrogen, these 2 electrons, which belong to the valence shell of nitrogen, but they do not participate in the bonding, you call them as the non-bonding electrons. And let me tell you, bonding electrons plus non-bonding electrons. Bonding electrons plus non-bonding electrons, you call them as the valence shell electron. You call them as the valence shell electron. Okay. My dear students, remember, molecule always acquires that shape. Molecule always acquires that shape in which the repulsions between the valence shell electron pairs are minimized and stability automatically is maximum. So basically, if I talk about the central atom here, that is nitrogen, this nitrogen has got bonding electrons as well as the non-bonding electrons, right? And bonding and non-bonding electrons combinedly are called as valence shell electrons. The molecule, it acquires that shape in which the repulsions between the valence shell electrons are minimized. And once the repulsions are minimized, stability is maximized. Number one. Number two, this is the order of the repulsions. Lone pair repulsions are maximum, followed by lone pair, followed by bond pair, bond. Right? Now, what is the important thing? The important thing is this. Whenever you have got a molecule, if in a molecule, central atom does not have any lone pair, if in a molecule, central atom does not have any lone pair, then remember, whatever is the geometry predicted through hybridization, whenever you see a molecule wherein the central atom does not have any lone pair, remember, whatever geometry is predicted through hybridization, that is going to be the actual shape of the molecule. That is going to be the actual shape of the molecule. Okay? Similarly, in the molecule, if the central atom has the lone pair, the geometry predicted through hybridization is not the actual shape of the molecule. These are the two things which I would want you guys to remember. Number one, in the molecule, if the central atom does not have any lone pair, at that point of time, whatever is the geometry predicted through hybridization, that is going to be the actual shape of the molecule. And if in a molecule, central atom has the lone pair, remember, geometry predicted through hybridization is not going to be the actual shape of the molecule. Now, let's try to understand this in detailed form. See, guys. First of all, let me talk about those molecules wherein steric number is 3. So, that molecule wherein the central atom has got the steric number 3. I'm talking about those molecules. Steric number means sigma plus lone pair. So, sigma plus lone pairs is equal to 3. And you know when the steric number is 3, hybridization involved is sp2. Hybridization sp2 means geometry, which is predicted through hybridization. That's going to be trigonal plane. So first of all, I'm going to talk about this particular molecule wherein the central atom has got the steric number. Now you tell me what all possible cases are there to have steric number 3. What all possible cases do we have to have the steric number 3? The first case is if the central atom is forming 3 sigma bonds and there is 0 lone pair. This is the first case. Sigma plus lone pair. Steric number will come out to be 3. The second case, if the central atom has got 2 sigma bonds and it has got 1 lone pair, again sigma plus lone pair makes it 3. So these are the 2 possible cases wherein the steric number can be 3. Now tell me one thing. If sigma bonds are 3, lone pairs are 0, what is the type of the molecule? The type of the molecule will be AB3L0. AB3L0. Here the type of the molecule will be AB2L0. Sorry, AB2L1. In both the cases, steric number is 3. And when steric number is 3, hybridization is sp2. So in this case as well as this case, in both the cases, hybridization is sp2. Now tell me one thing. Few minutes back I told you when the central atom does not have a lone pair, whatever is the geometry predicted through hybridization, that's going to be the actual shape of the molecule. And since geometry predicted through hybridization is trigonal planar, actual shape of the molecule is also going to be trigonal planar. And the molecule looks like this is AB3 molecule. AB3. And this geometry, this shape, I'll be calling as trigonal planar shape. All the 4 atoms are present on the same plane. All the 4 atoms are present on the same. Now, if sigma 2 lone pair is 1, the type of the molecule AB2L1. Hybridization is going to be sp2. Geometry predicted through hybridization, that's going to be trigonal planar. But what about the actual shape now? What about the actual shape? See what you have to do. Make the geometry first. Geometry was like this, AB3L0. This was the geometry. Now, do one thing. Remove one of the bond pair and put a lone pair instead. Now this becomes AB2L1. AB2L1, right? If you hide this lone pair, the molecule looks like a bent shape. And absolutely you call it as the bent shape. What shape you call it as? Bent shape. So AB2L1 molecule will have the bent shape. This is something which you have to remember. Okay. This was the first case. Those molecules which can have the steric number 3. Now, if the steric number is 4, steric number 4 means hybridization is sp3. Geometry predicted through hybridization is going to be tetrahedral. Geometry predicted through hybridization is going to be tetrahedral. Now let me check first of all what all cases can we have wherein the molecule will have steric number 4. The first case is if the central atom is forming 4 sigma bonds and 0 lone pair. The second case is if the central atom is forming 3 sigma bonds and there is 1 lone pair on. The third case is if the central atom is forming 2 sigma bonds and there are 2 lone pairs. First of all, tell me the type of each molecule. The type of this, the first molecule is AB4L0. This molecule is of the type AB3L1. This molecule is of the type AB2L2. AB2L2. Now, I told you already, when the central atom does not have any lone pair, geometry and shape, they are same. Geometry predicted through hybridization is basically going to be the actual shape. And you know, the shape is tetrahedral. This is AB4L0. AB4L0, right? AB4L0. Now, in case of AB3L1, what would be the shape? Shape won't be same as that of geometry because the central atom has the lone pair. So, do one thing. In this geometry, remove one of the bond pair and put a lone pair instead. Remove one of the bond pair and put a lone pair instead, right? And put a lone pair instead. This shape is called as pyramidal shape. If you hide the lone pair, it will look like a proper pyramid. So it's a pyramidal shape. AB2L2. What you have to do? Remove 2 bond pairs and put 2 lone pairs instead. So if I talk about the actual shape, remove 2 bond pairs and put 2 lone pairs. Let's say this A, this is B, and there is 1 lone pair here, there is 1 lone pair here. If you hide these 2 lone pairs, it will again be a bent shape, or you can call it as V shape. V shape or bent shape. Okay, so this was for those molecules wherein the central atom can have the steric number 4. Now, what if the central atom has got the steric number 5? Steric number 5. Hybridization would be sp3d. the geometry predicted through hybridization is going to be trigonal bipyramidal. Trigonal bipyramidal. Okay. Now tell me what all possible cases can we have to have the steric number 5? The first case, if the central atom is forming 5 sigma bonds, 0 lone pair. First case. Second case, 4 sigma bonds, 1 lone pair. Third case, 3 sigma bonds, 2 lone pairs. Fourth case, 2 sigma bonds, 3 lone pairs. These are all the possible cases. Now, first thing, tell me one thing. What is the type of this molecule? Type of this molecule is AB5L0. Type of this molecule is AB4L1. Type of this molecule is AB3L2. Type of this molecule is AB2L3. Okay. In the first case, where the central atom does not have any lone pair, geometry and shape will be the same. What is that? That is trigonal bipyramidal. Trigonal bipyramidal. How it looks like? This is A, B, one more B, one more B, and all these atoms are present on the same plane. You call this plane as the equatorial plane. Perpendicular upwards is 1B, perpendicular downwards is 1 more B, right? These three bonds are called as equatorial bonds, and this one and this one. These two bonds are called as axial bonds, right? Axial bonds, equatorial bond. And remember, axial bond length will be greater than that of equatorial bond. Axial bond length will be greater than that of equatorial. And this kind of the shape is called as trigonal bipyramid, because from the top, one pyramid is getting formed. From the bottom, one more pyramid is getting formed. This is what you call as trigonal bipyramidal shape. Now, AB4L1. What would be the shape of this molecule? Let me tell you, the shape of this molecule is called as seesaw. It's called as seesaw shape. What you have to do is just remove one of the bond pair and put a lone pair instead. So it looks like this. When you hide the lone pair, the shape is what you call as the seesaw shape, right? Now, AB3L2. The shape is called as T shape. AB3L2. So what you have to do is, you have to remove 2 bond pairs and put 2 lone pairs instead. So it's going to be like this. This is B. This is B. This is B. Here you have got a lone pair. Here you have got a lone pair. If you hide these 2 lone pairs, it looks like a T shape. Now, AB2L3. The shape is going to be linear. AB2L3. What you have to do is remove these 3 bond pairs and put lone pairs instead. So A, this is a lone pair, equatorial position, lone pair at equatorial, lone pair at equatorial. This is axial, this axial. Now, if you hide these lone pairs, it's going to be a linear shape, right? So these were the molecules wherein the central atom will have the steric number 5. Okay? Okay, guys? Is it clear to every one of you? All right. Now let's have a look on one more set of the molecules wherein the steric number is going to be 6. If steric number is 6, hybridization involved will be sp3d2. And geometry predicted through hybridization is going to be octahedral. It's going to be octahedral. Okay. Now let me show you what all cases can we have, what all possibilities can we have to have the steric number equal to 6. The first possibility is central atom forming 6 sigma bonds and there is 0 lone pair. The second possibility, 5 sigma bonds, 1 lone pair. And similarly, third possibility, 4 sigma bonds and 2 lone pair. Check the type of these molecules. This is going to be AB6L0. This will be AB5L0. Sorry, L1. This is going to be AB4L2. Okay. Now, central atom does not have a lone pair. That means geometry predicted through hybridization is going to be the shape. This is going to be the actual shape. And what is that going to be? That's going to be octahedral. So AB6L0. This is A. This is B. This is B. One more B. One more B. Okay, and one perpendicular upwards. Sorry, one perpendicular downwards. This particular shape is what you call as the octahedral shape. This is what you call as the octahedral shape, AB6L0 type. Now, if you look at AB5L1, AB5L1, the shape is going to be square pyramidal. Square pyramid. How it looks like? Do one thing. You can remove one of the axial bond and put a lone pair instead. Rest keep everything same. This is your AB5L1. Keep a lone pair. So this is your AB5L1. So this is square, and at the same time it's forming pyramid at the top. So it's square pyramidal base. It is square pyramid. It is square pyramid. Okay. Now, 4 sigma bonds, 2 lone pairs. The shape is going to be square planar. Square planar. And how it looks like? This is A. This is one more B. One more B. So it's a square present on the same plane. Perpendicular upwards will be a lone pair. Perpendicular downwards will be a lone pair. When you hide the lone pair, it will be a square planar shape. Okay. So this was for which molecules? Wherein the central atom can have the steric number of 6. Now there is one more left. What is that? What is that? Steric number 7. Steric number 7 means sp3d3 hybridization, and geometry predicted through hybridization is pentagonal bipyramid. Now let me tell you directly. Here you have got two cases. One is AB7L0. One is AB6L0. Sorry, AB6L1. Right? Geometry and shape here are same. And what do we call them as? You call them as pentagonal bipyramidal geometry. Here, the shape is going to be called as distorted octahedron. Distorted octahedron. So, my dear students, like this, from now onwards, you can talk about the shape of the different molecules. Now, tell me one thing. Tell me what is the actual shape of this molecule. The type is AB4L0. AB4L0 means tetrahedral. Tetrahedral shape. AB3L0 means trigonal planar. AB2L0 means linear. AB5L0, trigonal bipyramidal. AB6L0, octahedral shape. For example, AB3L1, pyramidal, right? This is AB4L0. AB4L0 is tetrahedral. This is AB2L3. AB2L3 means linear. Okay. This is AB2L3. AB2L3, again linear. This is your AB2L1. AB2L1 means bent. Okay. AB5L1 is going to be square pyramid. Perfect. So whenever you are given with any molecule, you just have to check the type of the molecule. Once you got the type of the molecule, you are sorted. You are done. All right, people. Is it clear? Is it clear to every one of you? Is it clear to every one of you? So easily from now onwards, you can check the shape of different molecules. You can check the shape of different molecules. Can you quickly tell me in the chats if all of this is like very clear to everyone? The resonance. Resonance is already taught by KK sir in your GOC. Perfectly done till here. All right, let's move on now. Let's move on. There is one more theory, my dear students. That's your molecular orbital theory. That's your molecular orbital theory. And in your molecular orbital theory, what kind of questions are asked? There are questions asked. There are questions asked based on the bond order. I believe all of you would be already doing that. In your molecular orbital theory, the questions are based on the bond order. The questions are based on the bond length. The questions are based on the stability, right? First of all, I'll show you the general process of solving the questions. Then at the end, I'll be giving you a shortcut also to solve those questions. Okay? I'll be giving you a shortcut also to solve those questions. Now, first of all, let's get to know what this molecular orbital theory is all about. My dear students, molecular orbital theory just says one thing. Molecular orbital theory just says one thing. First of all, at the time of the formation of molecule, what happens? The atomic orbitals of the bonding atoms, atomic orbitals of the bonding atoms, they combine, and they lead to the formation of molecular orbital. For example, let's say this is one of the hydrogen atom. There's one more hydrogen atom, and they have to form hydrogen molecule, right? Hydrogen is 1s1. So this is the s orbital of hydrogen. This is the s orbital of hydrogen. Now, as per MOT is concerned, these orbitals, these atomic orbitals of bonding atoms, they are going to combine. And once they combine, they will lead to the formation of what? They lead to the formation of molecular orbital. They lead to the formation of molecular orbital, right? They lead to the formation of molecular orbital. So in short, I'll say atomic orbitals of bonding atoms are going to combine. They will lead to the formation of molecular orbital. And remember, number of atomic orbitals combined is equal to number of molecular orbitals formed. So two atomic orbitals, for example, are combining here. So they will lead to the formation of two molecular orbitals. One is called as bonding molecular orbital. One is called as anti-bonding molecular orbital. Remember, energy of bonding molecular orbital is less. Remember, energy of anti-bonding molecular orbital is more. And if energy is less, you can say stability is more. If energy is more, you can say stability is less. So first of all, remember from now onwards, the atomic orbitals of the bonding atoms, they are going to combine. They will lead to the formation of molecular orbitals, right? They lead to the formation of molecular orbitals. And remember, number of atomic orbitals combined is equal to number of molecular orbitals formed, right? Perfect. For example, let's say this is the s orbital of one atom, this s orbital of one more atom, right? They are going to lead to the formation of two molecular orbitals. One is going to be your bonding molecular orbital. One is going to be your anti-bonding molecular orbital. Now let me tell you, S and S, they are going to do the head-on overlap. Head-on overlap leads to the formation of sigma bond. So one is called as, let's say if this was 1s, this was 1s, one molecular orbital is called as sigma 1s, one more is called as sigma star 1. Perfect, sigma star 1. For example, this is the 2p atomic orbital of one atom. Let's say this is 2pz. This is the 2p atomic orbital of one more atom. This is, for example, 2pz. Now they are going to combine. They lead to the formation of what? Molecular orbitals. Now it is pz, that means sigma. So it's going to be sigma 2pz, and this is going to be sigma star 2pz. One is called as bonding, one is called as anti-bonding, right? Similarly, if the orientation was like they were parallel, so one is going to be pi 2p, one is going to be pi star 2p. Okay? Perfect. Is it clear? Is it clear, people? Now, once the atomic orbitals are combined, they lead to the formation of molecular orbitals. Now, my dear students, after the formation of molecular orbitals, what we have to do is, we have to arrange the molecular orbitals on the basis of their increasing energies. Once molecular orbitals are formed, after that, we have to arrange the molecular orbitals as per the increasing energy. So I'll write it here. Once molecular orbitals are formed, comma, they are arranged on the basis of increasing energy. And once molecular orbitals are arranged on the basis of increasing energies, after that, filling of electrons in molecular orbitals is done as per Abbau's principle, as per Hund's rule, as per Pauli's exclusion principle. Once molecular orbitals are formed, after that we are going to arrange those molecular orbitals on the basis of their increasing energies, right? And then we are going to fill electrons in those molecular orbitals in accordance to these principles: Abbau's principle, Hund's rule, Pauli's exclusion principle. And once we fill the electrons in the molecular orbitals, then, my dear students, we can easily calculate bond order of a molecule. Bond order, what does that mean? That means number of bonds between two atoms. Bond order is number of atoms between two atoms. And how do we calculate bond order? It is simple. Half of number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals. Bond order is nothing but half of electrons in bonding minus number of electrons in anti-bonding molecular orbital. And remember, my dear students, if bond order in a molecule comes out to be 1, that means there's a single bond between two atoms. If bond order comes out to be 2, that means there's a double bond. There's a double bond between two atoms. If the bond order comes out to be 3, that means there's a triple bond between the atoms. And remember, at the same time, if bond order comes out to be less or equal to 0, that means molecule does not exist. That means molecule does not exist. Molecule does not exist. Okay, the molecule is non-viable. Now let me show you its application part. Or before showing the application part, remember one more thing. Remember, bond order is directly proportional to bond strength, right? Is directly proportional to bond dissociation energy, is inversely proportional to bond length. Anything can be asked from these things. Bond order is directly proportional to bond strength, right? Directly proportional to bond dissociation energy, inversely proportional to bond length. Inversely proportional to bond length. Okay. Now let's see how exactly all these things are done. See. First of all, these are the molecular orbitals. These are the molecular orbitals, right? And over here, I've arranged these molecular orbitals as far as their increasing energies are concerned. Over here, molecular orbitals are arranged on the basis of their increasing energy order. And you have to remember it in the same manner. This is the increasing order of the molecular orbital. This is the increasing order of the molecular orbital. And this increasing order of molecular orbitals is valid for those species in which the total electrons are less or equal to 40. This is the increasing order of the energies of the molecular orbitals, and this increasing energy order is valid for those molecules wherein the total number of electrons are less or equal to 14. Now, let's get to know how do we calculate the bond orders exactly. Try to understand, people, what I'm going to say. For example, you have got H2 molecule. In hydrogen atom, there is 1 electron. So 2 hydrogen atoms means 2 electrons. He2, in 1 helium atom, 2 electrons. 2 helium atom means 4 electrons. Li2, 6 electrons. Be2, total 8 electrons. Now, let's try to see. Every molecular orbital can accommodate a maximum of 2 electrons. So, these are 2 electrons. So, it is going to be sigma 1s2. Its configuration is sigma 1s2. Okay. 4 electrons, 2 here, 2 here. So, its configuration is going to be sigma 1s2, sigma star 1s2. Perfect. 6 electrons, 2, 4, and 6. 2, 4, and 6. So, it's going to be sigma 1s2, then sigma star 1s2, then sigma 2s2. Sigma 2s2. 8 electrons, 2, 4, 6, and after this 8. So, it's going to be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Okay. This is how you write the molecular orbital configuration. Now, if you got the molecular orbital configuration, you can easily calculate the bond order. You can easily calculate the bond order. How exactly? Half of number of electrons in bonding. Since this is the bonding molecular orbital, because anti-bonding is mentioned by star. Bonding. This is bonding, 2 electrons. Half of number of electrons in bonding minus anti-bonding 0. So 2 by 2 is 1. Similarly, it's going to be half of number of electrons in bonding, that's 2, minus number of electrons in anti-bonding, that's 2. The value comes out to be 0. Similarly, it's going to be half of number of electrons in bonding, that is 2 and 2, that's 4, minus number of electrons in anti-bonding, that's 2. So 4 minus 2 is 2, 2 by 2 is 1. Similarly, this is bonding, so 2 and 2 is 4. So it's half of number of electrons in bonding minus number of electrons in anti-bonding, that's again 4. The value comes out to be 0, right? So if the bond order is 1, that means there is a single bond between 2 hydrogen atoms, right? Bond order 0, molecule does not exist. Bond order 1, that means there is a single bond between 2 lithium atoms. Bond order 0, that means molecule does not exist. Perfect. And guys, at the same time, if you look carefully, every molecular orbital can accommodate a maximum of 2 electrons. So this already has 2 electrons. It can accommodate a maximum of 2 electrons. So do you see any unpaired electron here? No. Do you see any unpaired electron here? No. Do you see any unpaired electron here? No. So when the unpaired electrons are 0 in the molecular orbitals, the molecule is supposed to be diamagnetic. So this is a diamagnetic molecule, right? This is also a diamagnetic molecule. Similarly, let's move on and talk about the bond orders of other molecules as well. If you look carefully, guys, this is B2. Boron has 5 electrons. So 5 into 2 is 10 electrons. So it's a 10 electron species. Carbon C2 is 12 electron species. Nitrogen is 14 electron species. N2 positive is 13 electron species. N2 is 14. This is N2 positive. Take 1 electron out, 13 electron species. N2 is 14. Negative. Negative means gain 1 electron. So 15 electron species. Now, start filling these 10 electrons in these molecular orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? So, bond order will be equal to half of number of electrons in bonding 2, 4, 5, and 6 minus number of electrons in anti-bonding 2, 4. 6 minus 4 is 2. 2 by 2 is 1. 2 by 2 is 1. C2 molecule, 12 electrons. Already 10 are filled. Now one more here, one more here. Perfect. Because these are degenerate. They have got same energy. And pairing is not done in degenerate orbitals until both the orbitals get 1 electron each. Right? So if I talk about the bond order, it's going to be half of number of electrons in bonding right now. This is 2, 4, 6, and 8 minus anti-bonding 2, 4. 8 minus 4 is 4. 4 by 2 is 2. So its bond order is 2. N2, when you calculate it, similarly, its bond order will come out to be 3. Right? Since it's a 14 electron species, till now we have filled 12. 12 and 2 is 14. When you calculate, its bond order will come out to be 3. Now 13 electron species. When you calculate, when you write its molecular orbital configuration, you'll find it as 2.5. 15 electron species. Its bond order also you'll calculate as 2.5 only. Now you must be thinking, if this is the 15 electron species, and this particular increasing order of energies is valid for up to 14 electron species, then why am I using the same order for this one? It's a 15 electron species, and this order is used for all those species in which the total number of electrons are less or equal to 14. Then why am I using it for here? Since it's a 15 electron species. No doubt it's a 15 electron species, but its parent molecule is N2. That is 14 electron species. So that's the reason why I'm using the same energy order for this one as well. Okay, I have to check the parent molecule first. Parent molecule comes in this category. Therefore, N2 negative will also come in this category. Okay. So this was how to calculate the bond order for those species which have got electrons less or equal to 14. Now, what if electrons are more than 14? Then this particular order has to be filled. This particular order has to be remembered, guys. Okay, this particular order has to be remembered. So first of all, for example, you have got O2. Okay, before talking about O2 and stuff, remember this particular molecule C2, since it has bond order 2, so it's supposed to be C2 like this. And remember, this is a special case wherein both the bonds are pi bonds. Otherwise, normally what happens? If you have got a double bond, in a double bond, one is going to be sigma, one is going to be pi. But here, this is the special case wherein both the bonds are basically your pi bond. Okay, wherein both the bonds are basically your pi bonds. Now, let's move on to other molecules. O2 is a 16 electron species. This is a 15 electron species, O2 positive. O2 negative is a 17 electron species. O2 di-negative is 18 electron species. Now start filling these electrons in these molecular orbitals. So 16 electron species. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Regenerate. 11, 12, 13, 14, 15, 16. Now, if you look at this molecular orbital configuration, do you see unpaired electrons? Yes. So it's going to be paramagnetic. 2 unpaired electrons. 1 in pi star 2px, 1 in pi star 2py. Now calculate the bond order. Bond order is half of number of electrons in bonding. 2, 4, 6, 8, 10. Minus number of electrons in anti-bonding. 2, 4, 5, 6. 10 minus 6 is 4. 4 by 2 is 2. So its bond order is 2. Bond order 2 means there is a double bond between two oxygen atoms. Perfect. For example, O2 positive. O2 positive is 15 electron species. This was valid for 16 electron species. Now 15 electron species means take 1 electron out. If you take 1 electron out, and when you calculate the bond order, you will find out it as 2.5. When you calculate its bond order, this will be 1.5. And when you calculate its bond order, this will be 1. Okay. Now guys, I'm going to give you one direct trick which you are going to remember to calculate the bond order directly. Remember one simple thing. Whenever you see a 14 electron species, 14 electron species always will have bond order of 3. Then for example, 15 electron species, 16 electron species, 17 electron species, 18 electron species, or 13 electron species, 12 electron species, right? 11 electron species, 10 electron species. Okay, how do we calculate their bond orders? Do one thing. This was 3. Just decrease it by 0.5, so this will be 2.5. Decrease it by 0.5, this is 2. Decrease it by 0.5, 1.5. Decrease it by 0.5, this is 1. Again, decrease it by 0.5, this is 2.5. Decrease it by 0.5, this is 2. Decrease it by 0.5, this is 1.5. Decrease it by 0.5, this is 1. Perfect. So, these are the respective bond orders which you are going to remember directly from now on. You are going to remember them directly from now on. Okay? And guys, at the same time, there are a few more things which I'm going to tell you. CO positive. CO positive. CO positive. How many electrons are there? 8, 6, 14. 14 minus 1, 13. So technically, its bond order should be 13 electron species 2.5. But remember, this is the species whose bond order is 3.5. This is the only exception here. You are going to remember it as. You are going to remember it as. Okay. Perfect. Am I clear with this? Now guys, one more thing. I believe all of you remember about isoelectronic species. What are isoelectronic species? When you talk about the isoelectronic species, the number of electrons are same. In case of isoelectronic species, electrons are same. And remember, whenever you see isoelectron species, their bond order will also be same. Their bond order will also be same. Remember this particular point as well. For example, you have got CO. For example, you have got NO positive. For example, you have got CN negative. If you look at these particular species, right? 8 plus 6, this is the 14 electron species. 8 plus 7 is 15 minus 1, 14. So this is a 14 electron species. 7, 6, 13, and 14. This is a 14 electron species. So they are isoelectronic. That means their bond order will be same. And 14 electron species will have bond order 3. So all 3 have got the same bond order, which is equal to 3. Which is equal to 3. Remember this one as well. Guys, at the same time, which I want to discuss with you, what is that? You have got N2. You have got N2 positive. You have got N2 negative. You have to talk about their stability order. You know, bond order is directly proportional to stability. Bond order is directly proportional to stability. This is a 14 electron species, its bond order is 3. This is 13 electron species, its bond order is 2.5. This is a 15 electron species, its bond order is also 2.5. I have to give the order of stability. And you know, stability is directly proportional to bond order. Perfect. So which is maximum stable? The one which has got more bond order, that's N2. N2 is having maximum stability. Now among N2 positive and N2 negative, bond order is same. So how do we talk about the stability? Remember, when the bond order is same, then you calculate the number of antibonding electrons. If the bond order of two species is same, right? Calculate the number of antibonding electrons. That species which has got more antibonding electrons will be less stable. And when you check, N2 negative will be having more antibonding electrons than N2 positive. And you write their molecular orbital configurations. And then when you calculate the number of antibonding electrons, you will find N2 negative has got more antibonding electrons, so its stability will be less. So N2 positive will be more stable than N2 negative. Right? This is the order of what? This is the order of stability. So whenever you have got two species having same bond orders, then do one thing, calculate the number of antibonding electrons. More the antibonding electrons, lesser is going to be the stability. Perfect. Is it clear, guys? Let's have a look on one more topic, that is about the bond angle. Because there are a lot of questions wherein you have to arrange the molecules as per the bond angles. So let's have a look on exactly how do we arrange the molecules as per the bond angle. First of all, my dear students, in order to give the order of the bond angles, you just have to remember few things. And what are those few things? Try to understand. My dear students, the first thing always is going to be, whenever you have to arrange the molecules as per the bond angles, the first thing, you'll be prioritizing your VSCPR. You'll be using VSCPR. And by using VSCPR, if you find any molecule of the type AB2L0 or AB2L3, first of all, you'll be using your VSCPR. And by using VSCPR, if you find any molecule of the type AB2L0 or AB2L3, right? Since AB2L0, AB2L3, I've got linear geometry, bond angle will be maximum, that is 180. This is my first criteria always. Use VSCPR. If you find a molecule of the type AB2L0 or AB2L3, the bond angle is going to be maximum, that's going to be 180. If you are not able to check as per VSCPR, if VSCPR is not giving you the answer, then check the hybridization of the central atom. If the hybridization is different, for example, one molecule, the central atom has got sp, some other sp2, sp3. Now, you know, in sp hybridization, the bond angle is 180. In sp2 hybridization, the bond angle is 120. In sp3 hybridization, the bond angle is 109 degree, 28 minutes. If you are not able to decide as per VSCPR, then go for hybridization. If the hybridization of the central atom is different, then the one that is sp hybridization, its bond angle will be maximum, followed by sp2, followed by sp3. Now, if the hybridization of the central atom is same, then two things arise. If the hybridization of the central atom is same, what happens? If the hybridization of the central atom in all the molecules is same, then two cases will arise. Number one, if lone pair is absent on central atom, then give your answer as per hybridization. What does that mean? For example, you have got the molecule, let's say BCl3, you have got the molecule BBr3, let's say you have got the molecule BI3, right? Since there is no lone pair on the central atom, hybridization is same, sp2, sp2, sp2. Now, if hybridization is same and there is no lone pair on the central atom, then their bond angle is going to be same, right? That's going to be 120. Now, if the hybridization of the central atom is same, but lone pair is present, then remember, if lone pair is present at the central atom, then remember, bond angle is inversely proportional to the number of lone pairs. If hybridization is same, as well as the number of lone pairs on the central atom are same. If hybridization as well as number of lone pairs are same, then remember, bond angle is directly proportional to size of the surrounding atom. Also remember, bond angle is inversely proportional to the size of central atom. So you have to first of all remember this particular table, and now I'm going to show its application. First of all, you have to try answering as per VSCPR. Then go for hybridization. Then if hybridization is different, if hybridization is same, then check if lone pair is present on central atom. If it is not present, then give the answer as per hybridization. If lone pair is present on the central atom, then bond angle is directly inversely proportional to number of lone pairs. If hybridization as well as number of lone pairs on central atom is same, then bond angle is directly proportional to size of surrounding atom. Bond angle is inversely proportional to size of central atom. Let's try solving few questions which will make you master the concept of bond angle. See guys. For example, CO2, NO2 positive. Already the answers are given. What? Already the answers are given. Okay, anyways, we'll just still solve them. Anyways, answers are given. Still we are going to solve. First of all, CO2. CO2. Use the hybridization, use the VSCPR. The type of the molecule is Ab2L0. NO2 positive. When you check it, it is Ab2L0 again. This is Ab2L3. VSCPR says if you have got the molecule of the type Ab2L0 or Ab2L3, their bond angle is going to be maximum. That is 180. So all of them will have 180 bond angle. So their bond angles are equal. Okay, bond angles are equal. Now, check the hybridization. This is sp, this is sp2, this is sp3. Hybridization is different. Hybridization is different, right? Hybridization is different. And in sp hybridization, it's 180. Here it's 120. Here it's 109 degree, 28 minutes. So this is the order of the bond angle. Okay. Now, this is sp3. Even this is sp3. Even this is sp3. So same hybridization. Same hybridization. Now check if the lone pair is present on the central atom. No lone pair. One lone pair. Two lone pairs. If hybridization is same and lone pairs are present, then bond angle is inversely proportional to number of lone pairs. More the lone pairs, lesser the bond angle. More the lone pairs, lesser the bond. Right? Similarly, next one. This already I have shown you. This already I have shown you. Check this one. CCl4, SiCl4, GeCl4. Hybridization is sp3. Can you calculate? This also sp3. This also sp3. Central atom does not have any lone pair. If hybridization is same, central atom does not have any lone pair. Bond angle is going to be same. Give the answer as per hybridization. Bond angle same. Okay. Look at the next one. This is your sp3. This is also sp3. This is also sp3. Right? Even this is also sp3. Now lone pair on the central atom. There is lone pair on the central atom. And lone pairs are same. Lone pairs are same. Right? Lone pairs are same. Lone pairs are same. So, if hybridization is same, and the number of lone pairs are same, then bond angle is directly proportional to size of surrounding atom. Bond angle is directly proportional to size of surrounding atom. Bond angle is directly proportional to size of surrounding atom. Surrounding atom is also same. And bond angle is inversely proportional to size of central atom. So, lesser the size of central atom, more the bond angle. Lesser the size of central atom, more the bond angle. Look at this one. Again, look at the surrounding atoms here. Bond angle is directly proportional to size of surrounding atom. More the size of surrounding atom, more the bond angle. This is going to be your homework question. You can let me know its answer in the comment section. Right? So this is how you are going to arrange the molecules as per the bond angles. Right? Now there is one topic left here in chemical bonding chapter. What is that? That is going to be hydrogen bonding. Right? That's going to be hydrogen bonding. So my dear students, let's first of all check whether we have covered all the topics which I told you in the beginning itself. Okay, this is done, 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 formal charge is done, hybridization is done, this is done, this is done, bond angle is done. Now there is one small topic, that is your hydrogen bond. That's your hydrogen bond. Let's get to know what is hydrogen bonding and what all questions can be framed from hydrogen bonding. And the ones who are looking for the handwritten PDF and all, right, do join this Telegram group. I'll take not more than 10 to 15 minutes, and with that we'll be done. What is hydrogen bonding first of all? What is hydrogen bonding? What kind of questions can be framed from hydrogen bonding? My dear students, understand one thing. Understand just one thing. Just one thing. Just one thing. Let me just make you understand this from the basics itself. See guys, first of all, do you see this HF molecule? Okay, this is HF molecule, this is also HF molecule. If you look at the definition first, nitrogen, oxygen, fluorine, they are highly electronegative elements. We know it already. Nitrogen, oxygen, fluorine are highly electronegative elements. When they are attached to hydrogen, to form a covalent bond, the electron of the covalent bond, are shifted towards more electronegative element. The electron of the covalent bond are shifted towards more electronegative. The partial positive charge gets developed on hydrogen. The partial positive charge gets developed on hydrogen, and partial negative gets developed on fluorine. Now the partial positive of this hydrogen and partial negative of other fluorine, for example, there will be interaction between them, and this interaction is called as the hydrogen bond. Let's try to understand this a bit more in detail. This HF, right? It is a covalent bond here. Fluorine is more electronegative, delta negative, hydrogen delta positive, fluorine delta negative, delta positive. These are two different molecules. In this molecule, hydrogen got positive. In this molecule, fluorine got negative. Now there will be force of attraction between hydrogen of one molecule and fluorine of other molecule. And this force of attraction is what you call as hydrogen bond. For example, you have got water. Look at this particular one. OH. Oxygen will get delta negative, hydrogen delta positive. Oxygen delta negative, hydrogen delta positive. Oxygen delta negative, hydrogen delta positive. Oxygen delta negative, hydrogen delta positive. Now, the hydrogen of one water molecule and the oxygen of one water molecule, they are going to interact. This is a hydrogen bond. These two are going to interact. This is a hydrogen bond. Perfect. So what happens in hydrogen bonding? The more electronegative element of one molecule and the hydrogen of other molecule, they are going to interact and they are going to form which bond? They are going to form you here the hydrogen bond. As in case of your HF, as in case of your water, as in case of your NH3, right? Now there are two types of hydrogen bonds, please. One is you called as intermolecular hydrogen bond, intermolecular, and one is called as intramolecular. Intermolecular and intramolecular. Inter means between two molecules. Inter means between two molecules. Inter means between two molecules. Intra means within the molecule. Inter means between the two molecules. Intra means within the molecule. Now, for example, HF. As I told you already, there will be a hydrogen bond between them. So, hydrogen bond is between two molecules. So, this is inter. Water, inter. For example, carboxylic acids. This delta negative, this will be delta positive interaction. Here also they will have interaction. Because this will be delta negative, this will be delta positive. Similarly, this will be delta negative, this will be delta positive. So, it's a hydrogen bond between two molecules. So, this is intermolecular hydrogen bond between the two molecules. Now, if the hydrogen bond is within the molecule, you call it as intramolecular. Intramolecular. For example, this is OH. That means hydrogen will have delta positive. This oxygen will have delta negative. So, there will be interaction between them. So, this is hydrogen bond within the molecule. Intramolecular. Right? Similarly, there will be hydrogen bond between these two. Because this will be delta positive, this will be delta negative. Right? Similarly, this will be delta positive, this will be delta negative. So, this is within the molecule. Whenever you see hydrogen bond between two molecules, it is intermolecular hydrogen bond. Whenever you see hydrogen bond within the molecule, it is intramolecular hydrogen bond. Now, what are the consequences of intramolecular and intermolecular? These are something which you can remember directly. Solubility is directly proportional to intermolecular hydrogen bonding. More the intermolecular hydrogen bonding, more is going to be the solubility. Alcohols and glucose, they are soluble in water. Because what happens? When you put alcohol in water, it forms hydrogen bond with water. When you put glucose in water, it forms hydrogen bond with water. And which hydrogen bond? For example, if I'm introducing alcohol in water, so there'll be hydrogen bond between alcohol and water. So it's hydrogen bond between the molecules. So intermolecular. And more the intermolecular hydrogen bonding, more is going to be the solubility. Okay? Similarly, solubility is inversely proportional to intramolecular hydrogen bonding. More the intramolecular hydrogen bonding, lesser is going to be the solubility. Okay? And your orthohydroxybenzaldehyde, right? Its solubility will be less than that of para. Because in case of orthohydroxybenzaldehyde, there will be intramolecular hydrogen bonding, due to which all the sites, right, which were supposed to make hydrogen bonds with the solvent, they'll be already blocked with the help of intramolecular hydrogen bond. Okay? Similarly, few more applications. Viscosity is also directly proportional to intermolecular hydrogen bonding. So among these three, water forms more hydrogen bonding than that of this, I'll say intermolecular hydrogen bonding is more, viscosity is more, right? Air in hydrogen bonding is more intermolecular, right? So more viscosity. Similarly, melting and boiling point. Melting boiling points are directly proportional to intramolecular hydrogen bonding, right? So that's why this is the order here. Perfect. So remember these orders. And with that, we are done with the class 11th Inorganic, right? I know a lot of students are waiting for thermodynamics, which was missed in the last session. I'll be posting its recording tomorrow. For 1.5 hours, you can watch that. And so tomorrow, I'll be posting tomorrow evening, thermodynamics, 1.5 hour lecture. All right? Guys, do one thing. Do revise this particular session again. Because after revising this particular session again, then only you can remember the things which I told you in the today's session. And let me tell you one thing. Apart from this, nothing is going to be asked in this class 11th Inorganic. I promise to you. Whatever questions will be asked in your NEET, they are going to be these topics only we discussed in the PDF. I'll be sharing on my Telegram. PDF I'll be sharing on my Telegram right after the session. Okay? And do let me know in the comment section if you actually liked the session, right? Whether you got benefited out of this session. I would want to see your comments in the comment section, right? Because that's something which keeps on boosting us too. Chalo, I'll be taking a leave with this. I'll see you guys tomorrow at 8 p.m. right? Because tomorrow we are going to do the question practice of this class 11th Inorganic on the Unacademy platform. And at the same time, I shall be sharing the link of that particular session on my Telegram channel. Chalo guys, take care. God bless you all.